薪火相传。1972年，阔别祖国26年后，李政道与夫人秦惠俊回国。周恩来总理在接见李政道时，希望他能帮助解决中国人才断层的问题。自此，他开始了长达半个世纪的奔走呼号，为我国在世界高科技领域占有一席之地，以及科技、教育和人才事业的发展做出了卓越功勋。李政道1926年出生于上海，1943年考入浙江大学物理系，1944年转入国立西南联大，曾师从叶企孙、吴大猷、王淦昌、束兴北等物理大师。1946年，李政道赴美国芝加哥大学学习，师从费米教授。1955年，年仅29岁的李政道成为哥伦比亚大学建校200多年历史上最年轻的正教授，并开辟了弱作用中的对称破缺、高能中微子物理以及相对论性重离子对撞物理等领域。1956年，李政道与杨振宁共同提出宇称不守恒理论，获得1957年诺贝尔物理学奖，开创华人获得该奖项的历史。从上世纪70年代开始，李政道和夫人开始回国访问。1974年，李政道受到毛主席接见，除了谈论物理，李政道还提交了一份关于培养人才的建议书，建议选拔优秀青少年进行系统科学训练，成为少年班的雏形。1978年3月，中国科技大学创建了少年班。为推动我国物理学科建设和发展，李政道多方奔走，倾注了诸多心血。1979年4月2日，在邓小平、钱三强等老一辈领导人和科学家的推动下，李政道为来自全国100多个科研单位和高等院校1000多名师生讲了第1堂课。此后2个多月的讲学引起国内强烈反响。1979年6月11日，讲学结束后，李政道又参加了他促成的中美高能物理联合委员会第1次会议，率先开启了物理学领域的中外合作交流。在目睹了当时祖国面临人才断档的严重危机之后，他发起并亲自组织了中美联合招考物理研究生项目。从1979年到1989年，卡斯皮亚培养了1000名青年科技人才，如今已成为物理学、生物学、信息技术、金融经济等各个行业的中坚。从1972年与周恩
喂 Okay. Good morning, everyone, ladies and gentlemen. Today we will have a very special event on a special day, the International Symposium on Modern Physics in memory of T.D. Lee. Thank you very much for coming. First, we will invite President of Chinese Physical Society and Director of T.D. Lee in Shanghai Jiaotong University, Professor Jie Zhang, to give our opening speech.
Thank you very much for the kind invitation So because I didn't prepare to give the speech in English, so therefore I made the transcript in English, but instead I will speak in Chinese, and also that to save a lot of time and space. Thank you. 我们各位老师、各位同学，Professor Norman Christ, and also other sort of invitees from overseas. 今天呢，我代表中国物理学会和上海交通大学李政道研究所和李政道图书馆来做这个开场报告，是非常非常的荣幸。我们今天呢，大家一起聚集一堂，我们来回顾李政道先生这样的一个物理巨擘他的100年人生。我们本来计划的呢，今年的一年的对李先生100年诞辰的纪念，是在去年的4月份就开始了。但是李先生呢，去年的8月4号，他的这个去世呢，应该说是把我们的这个对李先生的缅怀纪念和他的这个100岁诞辰，其实是提前了。在去年李先生8月4号去世以后，从全国的很多的单位、很多的个人都对李先生的去世进行了缅怀、怀念。另外呢，在那段时间里面，从8月4号到8月就是到8月22号。我那一段时间呢，也是第一次认真的把李先生他的324篇论文都阅读了一下。阅读了一下以后，我发现我对于李先生了解的太少了。因为李先生他的为人很低调，他基本上不讲他学术上做了什么工作。那么正是在那一段的时间里面，我想。其实李先生的影响是远远的超出我们这个国界的，所以在那几次的追思的活动当中，一共呢有252万观众通过线上线下参加了我们那些追思会，有27个主要的15个主要的单位参与，另外呢还有就是媒体27家媒体，然后到现在为止，在那一段时间里面有900篇重要的这个悼念的这个文章，所以这些呢都是寄托了就是世界上的物理学界以及社会对李先生的追思和怀念。特别的呢是这个 IOPAP 就是纯粹与应用物理国际的联合会以及美国物理学会也都参加了那次追思会。那么在那一段时间，我阅读李先生的这324篇论文的过程当中，我其实才知道李先生他的对物理学的贡献是远远的超出他1957年和杨先生获得因为热相互作用当中的那个与争不守恒得诺贝尔奖，远远的超出那个。因为他呢是在量子场论、基本粒子理论、核物理、统计力学、流体力学和天体物理这些方面都有开创性的贡献。除了1957年那个诺贝尔奖之外，他的工作还直接的对另外的5个诺贝尔奖做出了奠基性的贡献。那么这些呢都在那5个诺贝尔奖获奖的发言或者是他们的那个重要的论文里面都提到了。所以呢，应该说李先生呢对于物理学的这个发展的影响呢，是远远的超出我们每个人对于李先生的这个了解。所以今天呢是一个非常好的一次机会，我们从科学精神的角度，我们来对李先生呢做一个全方位的一个回顾，同时呢是对李先生的这样的一个精神怎么样的一个传承，可能我们大家来一起来进行探讨。另外一方面呢，就是从8月4号到8月底那一段时间，正好是奥运会期间。 但是因为李先生的去世，因为各种各样的悼念的这个文章，所以呢，使得一批20岁到30几岁的年轻人，他们的眼光从奥运会上脱离开来，来认真的去看李先生的这些追思的文章。我也在问其中的一些年轻人，我说：“李先生，你们应该都是知道为什么你们现在感到这么震动。”后来他们说：“我们原来以为李先生就是一颗巨星，虽然非常亮，但是离他们很远。但是看了这些追思文章以后，他们才意识到李先生即使到今天也影响着我们千千万万个家庭的轨迹，当然也影响到了他们。所以这个呢，也是在那一段时间里面，我们中国的另外的一代年轻人，他们也对李先生应该是有了更加深刻的这个了解。那么接下来呢，就是我们从去年的李先生的生日开始，到今年的李先生的生日，我们这1年的时间，我们一群，我们组成了一个学术委员会，我们一起呢，对李先生的100年的他的各方面的这样的一个贡献，我们做深刻的研讨，希望呢把李先生点燃的这个星火，在全中国甚至在全世界永远相传下去。我们第一场活动是在李先生的生日2024年的11月24号，在苏州大学举办的。在那场会上呢，主要是对李先生的从小到他成长的这个经历，叫格物、正道、耿叙、荣光，做了追思和探讨。今天呢是非常感谢由高能所、北大理论所、物理所、CCAST 还有北大的高能物理研究中心的共同举办了这次对李先生的学术思想的研讨。在今年的6月28号到7月2号，还有一次呢是由浙大和中科大分别呢在杭州和合肥举办的，主要是对李先生的育人的方面他做的事情进行回顾和研讨，其中呢有大量的就是卡斯皮亚的学者都会参与。今年的最后一场呢，还是在上海交大，就是也是在他生日的前一天，举行天娱、解道、科艺、育婴。我们希望的到那个时候，我们把这1年的对李先生的100岁诞辰活动，它的精华，集中到那个会上，我们在全方位的对李先生从多个角度去进行回顾。另外的，作为我们这个活动的另外一个方面呢，是我们现在呢正在和央视的 CCTV 第4频道国家记忆合作。他们现在呢应该是从去年的那次我们的几次就是追思会就开始，他们已经开始介入，在收集片子。另外呢，现在已经完成了5次会面和2次100岁诞辰活动的这个记录。这个呢是准备在今年的李先生的这个生日，在全国来播放。另外呢，我和上海交大的李政道图书馆、李政道研究所的同事，我们实际上这就是我有感于在那一段时间里面，我读了那些文章以后，其实我意识到我对李先生了解的太少了。一方面的原因是因为李先生的低调，另外一方面是李先生他的活动的范围非常的广，除了科学，除了卡斯比亚以外，他还有大量的这种社会的活动。所以我们希望呢是全方位、多角度的对李先生他的一生做一个回顾。所以呢，这本书的名字呢就是展名叫《全景李政道》，就是我们希望的是一个除了有一些就是以前从来没有大家没有就是在公开场合传播的一些细节以外，更多的呢是一个全方位的一个全景式的一个描述。那么这本书的第一部分就有点像我刚才展示的那2个折页以外，是有3个折页，通过这3个折页， 社会上的人，任何人看这本书，他马上就了解了李先生的基本的情况。那么第二部分是详细的评述，主要是按照时间的这个顺序，把李先生的3个阶段，他的成长经历以及他的学术成果，还有呢对中国科教事业所做出的贡献，把它做全方位的展现。最后呢是把我们到目前为止收集到的所有的这些有关的新闻报道啊、研究成果、代表性追思文章，还有他回国的这个年谱，还有李政道论文年谱，做一个文献的一个记录。所以这个呢是我们现在已经开始做了，已经开了2次我们的这个作者的这个研讨会。那么最后呢，我想用这张片子结束我今天的这个开场白，就是李政道先生呢以毕生的追寻诠释了科学精神的纯粹和壮美，这也是我们今天的主题。他在微观世界解构对称的玄机，与家国山河浇筑科学的根基，更以赤子之心为后世立起精神的丰碑。那些穿越时空的智慧，始终叩问着每个求知者，如何让真理之光永驻人间，如何以探索的热望照亮文明的苍穹。此刻，当我们在此碰撞思想，追求问知，先生的科学思想便化作头顶不灭的星光，他的家国情怀已凝成大地温暖的灯光。愿这场跨越时空的对话，让他的风骨和哲思永远闪耀在人类向真理远征的星河之上。谢谢大家。
Thank you, Professor Zhang, for this opening speech. So next, we will have our first talk by Professor He-Shen Chen, the former director of IHAP Academician of CAS.
Good morning. I would like to take this opportunity to report to you Professor T.D. Li and his great contribution to China high-energy physics. T.D. is a world-renowned physicist who has made great contributions to the physics in the 20th century. As a Chinese descendant, T.D. has dedicated immersed effort to development of the science, technology, and education in China, particularly in high-energy physics and the cultivation of talents. Today, I take this opportunity to reflect on the pivotal role and historic milestones of the TD's contribution to the development of China high-energy accelerator. This is my outline. BEPC, China joined the SSC, BEPC2, and promotion synchronous radiance facility in China. In the September 11, 1992, Prime Minister Zhou Enlai made an important statement. He pointed out the initialization high-energy physics research in China and the preparatory work on the particle accelerator in China should be started immediately. And this according to this decision, the Institute of High Energy Physics has established in Beijing. And a few months later, 1 month later, Zhou Enlai warmly received the TD and his wife, who were returning mainland China after 26 years. I think that's the coherent arrangement by Prime Minister Zhou Enlai. I would like to mention one important meeting. In the May 24, 1974, Zhou Enlai met TD and his wife. So the does it work? Oh, sorry, this one. They discussed the TD emphasized the importance of science, technology, and education for national development. He proposed a special education program for young talents to study the fundamental research. The gang of four are in the reception, and also Mr. Deng Xiaoping is in the reception. So TD has a big fight with the gang of four, insisting his point of view. I think at that time, this is a very important issue to recover the science and technology in China. Also is good support to the effort of Prime Minister Zhou Enlai to recover the science and technology in China. I think this is an important page in the history. In the May 24, Chairman Mao met TD and accepted his proposal to setting up a safe special education program for the young talents. In the November 1977, Yuan Jialiu, Li政道, Wu Jianxiong, they wrote a letter to Zhang Wenyu, the director of the IHEP, and discuss what's the strategy for Chinese high energy physics accelerator. At that time, the dominant opinion in China is to build a proton machine in the Changping high energy proton machine. And the TD point out the proton machine has such kind of the high energy proton machine can cover the most of lower energy proton machine physics topics. China has not possible to build a bigger proton machine at that time. TD, Wu Jianxiong, and Yuan Jialiu, they suggested to build a E plus E minus collider, because E plus E minus collider has everyone has their own energy reason, special emphasis in particular physics topics. That's we could do it with limited resources from China and produce world-class results. In February 1979, Mr. Deng Xiaoping visited the US and signed the cooperation agreement in science and technology with the President Carter. Under this program, under this agreement, Mr. Fang Yi, the Deputy Prime Minister, and signed the agreement on the cooperation between the PRC and the USA in energy physics. TD played key roles in signing the agreement, and the annual meeting between the China and the US on high energy physics since June 1979, lasted for 38 years, play important roles to promote the particle physics in China and the collaborations between the US and China. In the March 19, 1981, TD wrote a letter to the IHAB director Zhang Wenyu and proposed clearly to build a 44.4 GeV electron positron collider. He pointed out please make a decision right away to build a E plus E minus collider with 4.4 GeV, the accelerator and detector. This is the what I described in the appendix. So at the current Chinese economy situation, in a lot of time is doing some adjustment. Within the current economy ability and the physics point of view, E plus E minus collider is the only possible proposal. I think this is very clearly made this statement, pointing out the particle physics development in China. In the July 18, 1981, TD wrote to Zhang Wenyu, since electron positron collider represents the new direction in China, it would be advisable to adopt this design of slug sphere that accelerate and detect Mach 2 as much as possible. This approach would help avoid any unnecessary detours. TD described the construction electron positron collider as a two birds with one stone solution, emphasize its influence from the three key perspectives. First, the project would enable important physics experiments in 1980s, allow China to quickly cultivate to a world-class team for high technology tolerant in the relatively short time. Second, collider synchron radiation capability would have a significant widening application in the scientific research. Third, the project allowed China's economy, capability, and expertise for the high energy physics at that time. In December 1988, during the meeting with the TD, Mr. Deng Xiaoping affirmed the decision to build the electron positron collider. He saying, we must made the firm decision and no longer delay. In the 1984 October, the Deng Xiaoping came to IHAB for the groundbreaking of the BEPC and meet TD and thanks his great contribution to BEPC. TD, the great contribution to the construction of BEPC. The construction of the BEPC was an unprecedented and formidable challenge for China. The China State Council established the leading panel, emphasized organizing hundreds of units, Chinese institutions, and companies to join the project. TD dedicated himself to supporting the construction of BEPC through the US-China High Energy Physics Annual Meeting, 4 major U.S. national labs were involved helping IHAB in the design, technology transfer, and a large number of scientists and engineers from IHAB were exchanged to the U.S. counterparts for specialized training. With great effort of the IHAB, in the October 16, 1988, the first correction in the BEPC was firmly observed, a major milestone for the BEPC. In the same morning, TD arrived at Beijing, welcomed by the director of IHAB, Fang Shouxian, and Ye Minghan. So this is a very important days for the BEPC. In the October 24, 1988, Mr. Deng Xiaoping attended the inauguration ceremony in BEPC. He visited the collider and delivered famous speech stating that China must secure a place in the world high technology. He expressed his gratitude to the TD's outstanding contribution to the IHAB, to the high energy physics in China. This is the birth fuel of the BEPC. Beam energy is 1 to 2.8 GeV, luminosity 5 times 10 to 30 at 1.55 GeV. Is factor 2 more than speed of slug, which start operation. The Mark II physicists joined the best collaboration. The best obtained many important results. This result is a process measurement of tau mass, doing it E plus E minus the tau pair production at the threshold. So this is a special method in the threshold. So we reduced the tau mass uncertainty significantly. So the result is 4.2 GeV below the value of the PTG, and approved lepton universality for the standard model. So together with the tau lifetime measurement in the lab. The construction of the BEPC provided China with their own high energy physics base. Without the vision of relentless effort of TD, it would be impossible to finish the construction of BEPC and secure the foothold in the global high energy physics. From the selection of its physics objective to determination of the accelerated design, from the engineering plan to the procurement of key equivalents from the US, from the training talents to the project manager, and from the physical research to international collaboration. Every aspect of the project was imbued with TD's dedication and hard work. The successful construction and the fruitful achievement of BEPC marked the beginning of the era of the China in the construction large-scale scientific facility, laying a solid foundation for the country's advancement in science and technology. Second, I would like to brief the history of China joining the SSC project. Many young people doesn't know this story. In the July 1989, the US government decided to build a superconducting supercollider in Dallas with a budget of 11 to 15 billion. Russian, Japan, India, Germany, and China joined the cooperation. The success of BPC show the research capability of Chinese physicists and the manufacturing capability in the relevant industry. It was used as the solid example by TD to persecute U.S. government to involve China physicists and in the international cooperation. With the help of TD, in the earlier 1993, China officially joined the project, contributing the Chinese products as the investment. Not a cash contribution, but just with our products. China's participation in the construction of SSC was a great opportunity to engage in the front scientific research, which had a significant enhance in the country's scientific research capability and high tech. In the earlier 1993, with the suggestion of TD, State Council organized a leading group for SSC cooperation. Vice Premier Zhu Rongji as the head of the group. 24 Chinese research institutes and companies participated in the project, most of which has involved in the development of BPC and had extensive experience in the collider equivalents. For instance, the Lin Zhongtang is the Minister of Aerospace, personally participated in the optimized magnet support design and save a lot of budget. Some of I have a physicist and engineer joined the design and the construction of SSC, went to at Dallas. In October 1993, the U.S. Senate and House decided to terminate the SSC to reduce the budget deficit. This decision would severely impact the global high-energy physics research. After the shutdown of SSC, U.S. Congress agreed to allocate $64 billion for compensation. So the Chinese companies and the institute also received compensation. BEPC future development. There was 2 stages. First is the BEPC improvement project. After BEPC returned good results, the Chinese physicists and government would like to further improve the BEPC performance. In 1993, Chinese Academy of Sciences approved the $34 million for the improvement project, which with help from TD. The upgrade project mainly including the increased beam energy to NILAC beam energy to 1.5 GeV. This could be full energy injectable JPSI and double luminosity and upgraded best detector called best 2. TD gave very strong support and arranged Professor Moret-Tigner to work at IHEP as the senior advisor. But this project had some difficulties in the cholesterol of NILAC, luminosity of storage in, and the best 2 detectors. And at that time, I have many difficulties, budget shortage, talent loss, and uncertainty in the roadmap. So with the greater effort of IHEP team, by the end of 1998, we solved the problem the Lilac energy reached the designed goal, luminosity increased by factor 2, and the detector problem solved. February 1999, the improved project reached the design goal and passed the assessment of CAS. And the spring 1999, the process measurement of R value carried out, so give a large international emphasis. IHAB has get out the setback. So this is the measurement of the R value. So they has large impact in the particle physics. The Higgs mass calculation consistent with measurement. Before that, the prediction was inconsistent with the measurement. And the large improvement in the muon G minus 2, and also for test peripatetic QCD. So for the long term of the BEPC development, there was a lot of discussion for the future plan. The Chinese climate sciences wish I have to be the third generation light source. And I have none afterwards to upgrade the BEPC. And I have a focus on the Taoqiang factory and submit the Taoqiang proposal. So in the 1995, Shanghai took the third generation light source over. And the proposal of Taoqiang factory could not receive support from Chinese academic sciences, including the debates on the physical cost, feasibility, and so on. So at that time, we proposed the BEPC2, used the pleasure and multiple bunch scenario-based research experience to increase luminosity by 10 with 400 million renminbi. And we submitted the proposal at July 1997. And according to the requirement from CAS, we prepared the first report called China High Energy Physics Development Strategy, so which suggests the upgrade BEPC is the future plan. Focus on the charm physics in the GFSI family region, where the luminosity, where the cross-section is very high, and promote non-accelerated physics, and push the multiple discipline platform. In the meeting, and also the Chinese Garden Sciences asked the additional support to BEPC to increase the operation budget and the critical equipment improving. We will make a significant improvement on the operation performance and collect 50 million GFSI in 3 years. And in the June 1999, the Chinese academic sciences submitted this report to the 5th meeting of lesson leading group of science and technology. TD gave strong support. The meeting decided further in deep study the roadmap and give 25, increase the BEPC budget, operation budget from 27 to 50 million, and provide 30 million every year for BEPC improvement. This is really a charcoal in the slope. So, and the BEPC carry out the commitment, performed, improved significantly, and 58 million GFSI events collected within less than 2 years. The BEPC2 is based on the very rich physics. So the hadron formic, the QED, and the light hadron spectroscopy, gluonic, exotic state physics with tau lepton, and looking for X, Y, Z particle, charm mesons, and the charm baryons. TD has highly concern with the roadmap I have in China and provide guidance and support. He consistent and in-housely support any initiative that could promote the high energy physics in China. He supported suggestion of Tau Chan factory in the 1950. And when he realized that the Tau Chan factory is not possible, in the July 1998, he wrote to Zhu Rongji, if there is no any recent breakthrough in the field of high energy physics, I don't believe there is necessary to build a Tau Chan factory in China. TD emphasized matters with the country, matters within the country should certainly be decided by domestic scientists and relevant leaders. I will not, nor do wish to, impose my view on them, as long as the decision they made by domestic leadership and scientists, even if I personally feel from a scientific perspective that is not best solution, I will support it to do the best of my ability within the boundary of the scientific principle. I think that's his the standard view to the help high energy physics in China. So I have made a second report, and reported to the 7th meeting, which including the BPC2 and the non-accelerated physics, including the cosmic ray, astrophysics, and the neutrino physics, and promote international collaboration, and build the Shanghai light source and the spallation neutron source, and promote the multiple disruption platform and applications. So the meeting agreed with the CAS report in principle, and agreed with 400 million yuan for the BPC2. TT has strongly supported the high energy physics development strategy. In October 1999, I reported the first report to TT and received his support. He emphasized the importance of non-accelerated physics experiment and the necessity of actively participation in large-scale international collaboration. He also promoted construction of synchronous radiation facility. In October the year 2000, I repeated the second report. He highly formed this report and believed this report provided a well-structured plan. He will actively organize the U.S. National Lab to support the design and R&D and BPC2. But we certainly need a competition from CSIR. CSIR decreased the beam energy, competed with the BPC2. And CSIR is the home of the pressure scenario. And we cannot compete with CSIR, with pressure scenario in the schedule and in performance. And at that moment, we decided to go to doubling design, which is adopted large crossing angle design in the KKB. So we increase luminosity to 23 and use superconducting magnet and improve the synchrotron radiation. And this is a big challenge, technical issue, and the funding increased by 60%. In the June 2001, I reported the TD, the double-ring design, and the challenging we face. TD explicitly support the scenario and emphasize the transition of CSER to the charm physical energy region demonstrated the importance of the charm physics, confirmed our development strategy is correct. Commutation bring more benefit than drawback. It pushes us to work hard, arrange. They also attract the attention for the international community and allow to mature verification of the significance of achievement. And he will use US-China cooperation meeting to support. He said life is interesting. I have a master favor in this commutation. With his support, we were in conference for the double-ring design. More important, he wrote a letter to Zhu Rongji, to Ministry of Science and Technology and the National Science Foundation, and so on, convinced them to increase the budget of BEPC from 400 million to 500 million. And I have used the previous 30 million 3 years to pay the 100 million money. Then we solve the money problem. So this is the BEPC tunnel. Tunnel was narrow and shorter. It's very challenging to design and construct. This is the collision reason, the detector and the many superconducting magnet. TD went to the tunnel to see this superconducting inside the magnet, very complicated, world smallest, built with his support from the beam air. And in June 2005, he visited Beijing Spectrometer Hall, congratulated the successfully joined the excitation of the 3 superconducting magnets. BEPC2 and BESS3 were finished on schedule and reached the design. So in March 2008, we reached the design luminosity, and the Clio closed and joined the physicist of Clio C joined the BESS3. TD wrote a letter to Congress. This is the international collaboration, and the BESS has a large improvement, large results from until September last year. They have more than 600 papers published, and the PRL paper more than 120. And they have they've discovered 30 new hadrons, and particularly exotic hadrons from 10 billion J-psi events, like a ground-rich process, which could be a global and many other very important issues. Finally, I would like to briefly report on the TD promote the synchrotron radiation facility. As I mentioned before, from the very beginning, TD already suggested BEPC with the synchrotron radiation. He said, I and many physicists consider collapsing 2 birds in the one stone solution. And he pushed the Beijing synchronous radiation facility and supported the talents training. And Beijing synchronous radiation facility has this is a sketch with the 16 beam lines, and the number of domestic user institutions is more than 300. International 36. 43,000 hours for the beam line, 12,000 experiments come out, and 10,000 research papers published. This is some highlighted results. I will not read it. And for the Shanghai light source, so in February 95, TD wrote to Shanghai Mayor Xu Kuangdi, strongly support the Shanghai light source. He thinks it's the most widely applied high technology project with immense potential. And he made many suggestions and training people for the Shanghai light source. He said, I fully supported a large-scale synchronous radiation source aligned with the national rapid development and growing needs of applied science and technology. Shanghai is my hometown, and I sincerely hope it became one of the bases for China's science technology advance in the 21st century. This is the sketch of the Shanghai, and the 34 beam lines, 46 experience stations, and the users more than 100K. And user the top tier paper is more than 200. This is the list of results. Never forget the well digger when drinking water. Just TD's contribution to the 20th century physics has been inscribed in the annals of physics. His contribution to the China Hanley physics and the mega science facility will, however, be recorded in the history of physics of China. So, with his fascinating insight, TD eliminated the most optimal path for height in China per both E+, E-, and Chang physics, guiding the rapid progress over 4 decades. China has evolved from the screwing a food hand to the important player in the world high energy physics stage. BEPC has become an evergreen tree in the international high energy physics for 40 years. TD farsight advocated and deployed the dual use of BEPC and also pushed the Shanghai light source. The light source became an important unit of the national science and innovation system. His dedication to science, pursuit for truth, love for and development to his motherland are example for us to follow. Constantly educating and inspiring us to unit and strive for the new glory to China high energy physics. On November 24th last year, the ashes of TD was buried at the Suzhou Cemetery, where he now rests entirely on the soil of his beloved motherland. The cemetery is distinguished by the 4 sculptures. This symbolized his proud contribution to both physics and art. These sculptures are testament to his enduring legacy will forever stand as his completeness in his place of entire rest. Thank you.
Thank you, Professor Chen, for this comprehensive review on TD's contribution to the Beijing Electron Positron Collider and the synchrotron radiation. So our next speaker is Professor Shoji Nagamiya from KEK and Recon, and he's online. He did plan to come in person, but due to emerging health issue, so can only report online. So, yeah, Nagamiya-san, are you online now?
Yes. Can you
Okay.
see?
Okay, we can see you and we can hear you. Thank you. Please start.
Okay. Thank you very much for your invitation. I apologize for the inconvenience on the video because I had a unexpected accident to break a bone in January, so I could not come. My talk is Professor T.D. Lee's memory and his contribution to heavy ion physics. I want to call him TD from now on instead of calling him Professor T.D. Lee. CCAST is a place where we visited very often, and T.D. Lee also invited me to his special restaurant at the CCAST. And it was a very memorable place. My first encounter with a TD was in 1974 when I was 30 years old. He gave a talk in Berkeley on the Lee-weak matter. I saw him for the first time, but of course, he did not know me. Lee-weak matter is a prediction that at a very high density nuclear matter, there would be a state where a nuclear mass is zero, a very challenging model, and it will be described later by Horst Stocker. This year, he organized the Bear Mountain Heavy Ion School, which is the initiation of him to be involved in the heavy ion physics. In 1983, a big high-energy physics project of a 400 GeV proton collider called Isabel was terminated, was turned down due to the SSC at the Brookhaven National Laboratory. T.D. Lee sympathized with it, but proposed that Nick Samius, the director of Brookhaven National Lab, convert this existing ring into a heavy ion beam collider. Now it is called a RIC. In this year, the Cork Matter Conference was held at the Brookhaven National Lab, and the nuclear physicists supported the TD's proposal. The left side is a proceeding of the Bear Mountain Heavy Ion School, where many people are there. And the right side is Nick Samius on the left as the director of Brookhaven, and the TD together with another important person, Jack Sandwise at Yale, who echoed TD's proposal to convert Isabel to RIC. Around 1982 or 3, I returned back to Japan from the Berkeley and we proposed a heavy ion experiment at the KEKPS. However, in 1982 to 3, we proposed a heavy ion experiment at the KEKPS, but it was turned down a very few times. So in 1974, we decided to start an AGS heavy ion experiment at Brookhaven. Very luckily, in 1994, the Tokyo is the University of Tokyo now, and MIT and Brookhaven collaboration team was created. And I started to commute to Brookhaven from Japan very frequently. One day in June or July in 1985, Charlie Bolte at the Columbia University came to Brookhaven and invited me to Columbia University. At the Columbia University where I visited, immediately after my short talk, TDD suddenly showed me his apartment nearby the campus and asked Wang Li at the Columbia University at the same time to show me the houses in the neighborhood. I was extremely baffled, and perhaps this was TD's style of inviting a person to Columbia. And after many, many things, I decided to become a professor at the Columbia University in June 1986. 1986, when I arrived at the Columbia, there was TD's 60th birthday celebration and the 30th celebration of the parity violation. On the left figure shows that TDD and Chen Xiang-Wu and her husband Luke Yuan and Tai Yu-Wu, and Tai Yu-Wu was a supervisor of both TDD and CN Yang. And another photo on the right shows many Nobel laureates who came to this celebration. Chandrasekhar, Jim Cronin, I. Rabi, TD, and Samuel Tin, and many others like Letterman and Panofsky et al. Came. TD received the Nobel Prize in 1957 at the age of 30 to 31. He explained the he explained the concept of the parity using a blackboard to the public. Please remember this blackboard. This is very important. Oh, wait a second. Did I do something wrong? It's okay. Can you see?
Yes, we can see.
Ah, I have a little bit changed. Nevertheless, okay. I cannot. I cannot proceed anymore.
Please connect the screen, and then go to the next slide.
？
Okay.
？
Please click the screen, and then go to the next slide. ？
？
And then go to the next slide. ？ And then go to the next slide. ？ And then go to the next slide. ？ And then go to the next slide.
？
And then go to the next slide.
click the screen.
Yeah, your mouse seems not in the normal state. Click the screen.
I clicked it.
Or you may restart. Yeah.
Really?
Quit the presentation and then start again.
Okay. It's very strange.
Yeah, try it again. It seems okay now. Go to next page.
The next page, it goes to the.
Can you do that? That's the parity variable. Yeah.
The original one, it went very well, but can you click there? I don't know. Yeah, maybe you not.
Or can you use page down? The keyboard, page down.
There's something wrong.
Yeah.
I should have given to you my slide.
Take it easy.
How about this one?
Yes.
Can you see?
Yes. It's okay now.
Okay. Sorry, then I went there to here. Okay. In 1986, I'm sorry, this is by 1990. Okay. Okay. By 1990, it has been known that at the AGS studies, they showed that the colliding nuclei would stop each other at the AGS energies of 14 GeV per nucleon on a fixed target, namely it colliding nuclei stop each other, whereas it is expected that colliding nuclei are going to pass through and hot pionic matter would be created behind. In the famous temperature and density phase diagram, a dense matter would be created at the AGS, whereas it is expected that the zero density and very hot nuclear matter would be created at RIC. So RIC sweeps this region, and the AGS sweeps this region. In 1990, pre-discussion started on RIC experiment, like this photo, and in 1991, 4 proposals were submitted: STAR to measure 4pi, OASIS to measure dielectrons and photons, and dimuons to measure dimuons, and spark tails to measure dielectrons again. Of course, all the experiments measure the hadrons. The PSC result was that the STAR was approved, whereas the 3 other experiments were turned down and advised to combine together. TD was reasonably unhappy about this decision, partly because I was in the OASIS experiment, but later he kindly arranged a dinner for me with the Brookhaven management. Mel Schwartz here, the associate director at that time at the Brookhaven, and Nick Samuels here, and Janet Lee was sandwiched between these two, and half of my wife is here. In this way, in 1992, 3 proposals were combined under the name of Phoenix, like this bird. However, DOE covered only $30 million. KEK in Japan covered over $10 million for dielectrons and photons. But $10 million were missing for an additional dimuon. I decided to approach Riken in Japan again for dimuon. Fortunately, at the end of 1993, Riken started the spin physics program, which included the Siberian snakes and spin rotators. Also, we proposed a DOE for additional $10 million for dimuons. Very luckily, at the end of 1994, spin physics and dimuons were funded at the Riken. Immediately after that, in the early 1995, NSAC recommended, and NSAC is a Nuclear Science Advisory Committee in the United States, recommended approving our DOE proposal as a matching fund. Therefore, we had 2 muon arms, one from Riken, $10 million, and the other from a DOE, another $10 million. This is an entire assembly of the Phoenix detector after it's completed. These days, TD organized a very important workshop summarizing all the AGS accelerator activities. Mel Schwartz here, who discovered the muon neutrino, San-Lan Wu, on behalf of Sam Tin for JPSI, TD, and those 2 were for rare decay person, and one heavy ion person, which is me. Around these days, I was seeking a theorist on spin physics to support Riken because this program in the US was in the category of the high energy physics and not the nuclear physics related to the RIC physics. Therefore, I approached Bob Jaffe at MIT to support it from a theoretical side. He considered a while, but declined this task about half a year later. So I went to TD's office. TD's office is very close to my office. He was in front of my office to consult on who could serve in this position. But there were no solutions then. However, to my surprise, TD came to my office a few hours later and asked me, how about me to serve it? I was extremely confused and faxed the president at that time, American, Akito Arima, the famous nuclear physicist at RIKEN, to consult with him. At RIKEN, there were several discussions, and finally, President Arima offered TD as the first president of RIKEN BNL Research Center called RBRC instead of a theory consultant. The above is my very minor contribution to RBRC, but it introduced very successful operation of RBRC because TD introduced a joint appointment system with university and RIKEN, and also a joint, it's a very successful operation of RBRC because TD introduced the joint appointed system with the university and RIKEN, and as a result, many physicists have been born from RBRC. Also, RBRC nicely installed the spin rotators, snakes for star and phoenix experiment, and the very powerful dimuons for phoenix experiment. Finally, in public, RBRC is the most well-known and famous and successful US-Japan collaboration, mainly by TD. He created the symbol of RBRC like this, which I use very often in this slide. TD also asked his friend Lee Karen to symbolize heavy ion collisions at high energies for RBRC. This is a heavy ion experiment or something. However, I saw this near my neighborhood house in Japan. It must be a very famous one in China. RIKEN BNL Research Center, RBRC, eventually created many positions in the United States, Japan, and Europe. either director or professor and many others. Sorry about it.
Like Mia-san, probably you can close this window. I think the presentation is behind.
Yes, sorry. Then in 2007, TD received in Japan the Order of Merit of Japan, a very high-class award for his significant contribution to the Japan-US collaboration. The person on the right here was the president of RIKEN at that time, Dr. Ryoji Noyori, a Nobel laureate in chemistry in 2001. I described the relationship primarily to Japan, but TD contributed much other contribution to other countries, particularly to China. As an example, for the United States, very important program was the CASPIA, China-US Physics Examination and Application. Over 100 students per year were selected in China. Here, the competition was extremely high in China. Also, competition to obtain these students was also high in the United States. In addition, China supposed to prepare the position for them. The CASPIA program started in 1979. However, TD decided to terminate this CASPIA at the end of the 1980s and told me also, sadly, why. China had never prepared any positions in those days. By now, however, his effort of CASPIA was a great success because many leaders from China were born from CASPIA program. This is a slide in 2014. TD was very proud of inheriting his office from Hideki Yukawa at Columbia University. As he received the Nobel Prize, Yukawa received the Nobel Prize at Columbia before TD succeeded his office. After TD's retirement, however, this office was renovated. When I visited TD in 2014, his secretary took this photo during this renovation. His blackboard he used for the parity violation time is, however, now at Osaka University because Yukawa wrote his famous paper by Yukawa theory when he was in Osaka University. This picture shows TD's last post mail to me in 2019. when he was 93. It included a sketch of flowers in a park in San Francisco. His handwriting was very much like that as before. We all share the sad news of Professor T.D.D's passing on August 4 at 97 years old. His departure was a loss to the entire physics world and also heavy ion physics, and it was our personal void. We sincerely hope his profound legacy will continue to inspire generations and ensure that he will live eternally even after passing from the earth. Thank you very much.
Thank you, Nagamiya-san. And now we finished the first session, and we are behind schedule, but I think we should keep 20 minutes break for photo and a coffee break.
1972年，阔别祖国26年后，李政道与夫人秦惠俊回国。周恩来总理在接见李政道时，希望他能帮助解决中国人才断层的问题。自此，他开始了长达半个世纪的奔走呼号，为我国在世界高科技领域占有一席之地，以及科技、教育和人才事业的发展做出了卓越功勋。李政道1926年出生于上海，1943年考入浙江大学物理系，1944年转入国立西南联大，曾师从叶企孙、吴大猷、王淦昌、束兴北等物理大师。1946年，李政道赴美国芝加哥大学学习，师从费米教授。1955年，年仅29岁的李政道成为哥伦比亚大学建校200多年历史上最年轻的正教授，并开辟了弱作用中的对称破缺、高能中微子物理以及相对论性重离子对状物理等领域。1956年，李政道与杨振宁共同提出宇称不守恒理论，获得1957年诺贝尔物理学奖，开创华人获得该奖项的历史。从上世纪70年代开始，李政道和夫人开始回国访问。1974年，李政道受到毛主席接见，除了谈论物理，李政道还提交了一份关于培养人才的建议书，建议选拔优秀青少年进行系统科学训练，成为少年班的雏形。1978年3月，中国科技大学创建了少年班。为推动我国物理学科建设和发展， 李政道多方奔走，倾注了诸多心血。1979年4月2日，在邓小平、钱三强等老一辈领导人和科学家的推动下，李政道为来自全国100多个科研单位和高等院校1000多名师生讲了第1堂课。此后2个多月的讲学引起国内强烈反响。1979年6月11日，讲学结束后，李政道又参加了他促成的中美高能物理联合委员会第1次会议，率先开启了物理学领域的中外合作交流。
Hi, Shoji. I'm here.
在目睹当时祖国面临人才断档的严重危机之后，发起并亲自组织了中美联合招考物理研究生项目。
Are you doing good?
从1979年到1989年，卡斯皮亚培养了1000名青年科技人才，如今已成为物理学、生物学、信息技术、金融经济等各个行业的中坚。从1972年与周恩来总理讨论云南站宇宙线研究成果，并首次提出我国应考虑建造一个小型正负电子对撞机，到1979年写信给方毅副总理，提出关于培养高能实验物理学者的一些建议，积极推动我国加速器和实验物理方面的人才培养。再到1981年，亲自向邓小平同志介绍对撞机方案，李政道排除万难，亲力亲为，积极推动我国高能加速器的建设，为祖国高能物理事业谋求发展。在我国高能加速器建设方案经历7上7下的严重挫折时，为避免我国高能物理错过发展时机，李政道召集中美科学家一同研讨，提出符合国情的建设质心系能量为44亿电子伏特的正负电子对撞机，开展灿物理研究的建设方案。
中国这么一个国家呀，必须在高科技领域里边有一席之地，搞这个工程也就是这个意思。
1981年，邓小平批准建设我国第1台大科学装置——北京正负电子对撞机。从1984年动工到1988年建成运行，他押上了自己的声誉，利用自己的影响，创造各种渠道，全程参与并积极协助。2000年，高能所提出了我国的高能物理和先进加速器发展目标，提议对 BEPC 进行重大改造。李政道本着有利于祖国高能物理发展的初衷，一如既往地支持 BEPC-2的改造方案，并在因国际竞争态势发生变化、建设方案发生变化时，亲自出面多方沟通。BEPC-2 2008年开始运行，在灿物理、灿偶素、氢强子、量子色动力学等方面取得了大量成果，使我国在超灿物理领域持续保持国际领先。它为我国高能物理跻身世界前列做出了卓越贡献。在中国高能物理领域多个大科学装置和实验背后，都有李政道全力以赴奔走助力的身影。2003年，李政道在得知大亚湾中微子探测装置的建设计划后，并不以简单的立场或者关系来决定支持还是反对，而是投入大量精力，付诸实际行动，从科学的角度仔细研究，最终判断大亚湾中微子实验是一个好的实验。随后，他便全力推动项目在中国立项，为项目争取国内外资金，还亲自参与科研准备。2012年，大亚湾中微子实验精准测量了中微子混合角西坦13，证实了第3种中微子震荡模式。 大亚湾实验的成功，不仅为中国的科学家赢得了多项国际大奖，也为中国的粒子物理研究赢得了前所未有的国际声誉。自此，我国的中微子实验研究从无到有，并走到了世界前列。他还不遗余力地推动北京同步辐射装置、上海同步辐射光源、中国散列中子源等中国高能物理大科学装置的建设。如今，我国在高海拔和空间宇宙线实验、暗物质探测、X 射线天体物理研究等方面也取得了长足的进步。拉索高海拔宇宙线探测设施、慧眼、极目卫星取得重大成果，未来的空间探测卫星和空间站实验正在准备中。北京高能同步辐射光源、中国散列中子源等大型多学科交叉研究平台的建设和应用也从无到有，迅速发展，成为国家科技创新体系的重要单元，也逐步成为国际领先的实验基地。中国高能物理研究每取得有重要国际影响的成果，都会收到李政道发来的贺信。信中不仅肯定所取得的进展，更是充满真诚的鼓励、关爱和喜悦。从蹒跚起步到阔步前行，从跟跑、并跑到部分领域走到世界前列的跨越式发展，在李政道的持续关怀下，我国的高能物理事业走出了一条符合国情并战略性发展的道路。李政道先生为我国科技、教育事业和人才培养殚精竭虑，他倡导设立博士后制度、自然科学基金制度，捐资设立秦桧郡李政道中国大学生见习进修基金。他也力主建设北京现代物理研究中心、北大高能物理研究中心、中国高等科学技术中心、浙江近代物理研究中心、李政道研究所等基础科研基地，极大地推动了祖国科教事业的改革与发展。作为炎黄子孙，近半个世纪以来，他对养育了自己的祖国充满了深厚的感情和眷恋，为我国科技和教育事业的发展呕心沥血。如今，科技报国的火炬也正一代一代薪火相传。1972年，阔别祖国26年后，李政道与夫人秦桧郡回国。周恩来总理在接见李政道时，希望他能帮助解决中国人才断层的问题。自此，他开始了长达半个世纪的奔走呼号，为我国在世界高科技领域占有一席之地，以及科技、教育和人才事业的发展做出了卓越功勋。李政道1926年出生于上海，1943年考入浙江大学物理系，1944年转入国立西南联大，曾师从叶企孙、吴大猷、王淦昌、朔星北等物理大师。1946年，李政道赴美国芝加哥大学学习，师从费米教授。1955年，年仅29岁的李政道成为哥伦比亚大学建校200多年历史上最年轻的正教授，并开辟了弱作用中的对称破缺、高能中微子物理以及相对论性重离子对状物理等领域。1956年，李政道与杨振宁共同提出宇称不守恒理论。 获得1957年诺贝尔物理学奖，开创华人获得该奖项的历史。从上世纪70年代开始，李政道和夫人开始回国访问。1974年，李政道受到毛主席接见，除了谈论物理，李政道还提交了一份关于培养人才的建议书，建议选拔优秀青少年进行系统科学训练，成为少年班的雏形。1978年3月，中国科技大学创建了少年班。为推动我国物理学科建设和发展，李政道多方奔走，倾注了诸多心血。1979年4月2日，在邓小平、钱三强等老一辈领导人和科学家的推动下，李政道为来自全国100多个科研单位和高等院校1000多名师生讲了第1堂课。此后2个多月的讲学引起国内强烈反响。1979年6月11日，讲学结束后，李政道又参加了他促成的中美高能物理联合委员会第1次会议，率先开启了物理学领域的中外合作交流。在目睹了当时祖国面临人才断档的严重危机之后，他发起并亲自组织了中美联合招考物理研究生项目。从1979年到1989年，卡斯皮亚培养了1000名青年科技人才，如今已成为物理学、生物学、信息技术、金融经济等各个行业的中坚。从1972年与周恩来总理讨论云南站宇宙线研究成果，并首次提出我国应考虑建造一个小型正负电子对撞机。到1979年写信给方毅副总理，提出关于培养高能实验物理学者的一些建议，积极推动我国加速器和实验物理方面的人才培养。再到1981年，亲自向邓小平同志介绍对撞机方案。李政道排除万难，亲力亲为，积极推动我国高能加速器的建设，为祖国高能物理事业谋求发展。在我国高能加速器建设方案经历7上7下的严重挫折时，为避免我国高能物理错过发展时机，李政道召集中美科学家一同研讨，提出符合国情的建设质心系能量为44亿电子伏特的正负电子对撞机，开展灿物理研究的建设方案。
中国这么一个国家呀，必须在高科技领域里边有一席之地，搞这个工程也就是这个意思。
1981年，邓小平批准建设我国第1台大科学装置——北京正负电子对撞机。从1984年动工到1988年建成运行，他押上了自己的声誉，利用自己的影响，创造各种渠道，全程参与并积极协助。2000年，高能所提出了我国的高能物理和先进加速器发展目标，提议对 BEPC 进行重大改造。李政道本着有利于祖国高能物理发展的初衷，一如既往地支持 BEPC-2 的改造方案，并在因国际竞争态势发生变化、建设方案发生变化时，亲自出面多方沟通。BEPC-2 2008年开始运行，在灿物理、灿偶素、氢强子、量子色动力学等方面取得了大量成果，使我国在超灿物理领域持续保持国际领先。它为我国高能物理跻身世界前列做出了卓越贡献。在中国高能物理领域多个大科学装置和实验背后，都有李政道全力以赴、奔走助力的身影。2003年，李政道在得知大亚湾中微子探测装置的建设计划后， 并不以简单的立场或者关系来决定支持还是反对，而是投入大量精力，付诸实际行动，从科学的角度仔细研究，最终判断大亚湾中微子实验是一个好的实验。随后，他便全力推动项目在中国立项，为项目争取国内外资金，还亲自参与科研准备。2012年，大亚湾中微子实验精准测量了中微子混合角西坦13，证实了第3种中微子震荡模式。大亚湾实验的成功，不仅为中国的科学家赢得了多项国际大奖，也为中国的粒子物理研究赢得了前所未有的国际声誉。自此，我国的中微子实验研究从无到有。
Okay, please. Okay, let's start the second half of the morning session. And since we already far behind the schedule, I hope all the speakers should stay in the time sharply, okay? And we won't invite questions afterwards. I think that's to save some time. Okay, the first speaker is Professor Ji Xiangdong from Shanghai Jiao Tong University and Mainland University. Okay, Xiangdong, can you hear us?
Yes, I can hear you. Can you hear me?
Yeah, and now could also see the slides, but please full screen.
Yes, let me do this. Okay.
Okay.
Can you see
Okay.
slides?
Okay.
Okay.
Go ahead.
All right. Hi, everyone. I'm extremely honored to be invited to give this talk here. I'm deeply sorry that I can't be there, although I very much hope I can. Today, we're celebrating Professor T.D. Lee's scientific contribution to physics and other field. And my assigned talk is about parity violation that is considered as perhaps the most important contribution that TD made in physics. The title of my talk is Broken Parity and Biased Universe. And as we have heard from previous talks, that the TD, without question, is one of the most distinguished physicists in the 20th century and in human history. His influences and contribution to science development in one of the biggest countries in the world are unparalleled by any scientist. And I have personally benefited enormously from his teachings, generosity, and wisdom in my entire life. So here's the outline of my talk. I will start with my personal interaction with Professor Lee. And then I will move on to talk about this historical importance of discovery of broken parity. And following that, I will talk about its deep consequences and implications for particle physics and cosmology, and also something that we can see in our naked eyes on the Earth and the sky. And finally, I will make some comments. I started with my personal interaction with TD, and we have heard that TD initiated the COSPEAR program, helped 1,000 Chinese physics students to enter graduate schools in US. And I was one of the lucky ones. And I took part of the COSPEAR exam in the summer 1982 in Shanghai, upon recommendation by the physics department in Peking University. And I was recommended by the program in October 1982, and then went to Drexel University in July 1983 as a physics graduate student. And I have chosen nuclear and particle physics as my career. And so here I show some of my fellow COSPEAR students working in the area of nuclear and particle physics, and Professor Zhao Tianqi from University of Washington, who wrote a biography of TD, and if you haven't read it, then you should have. Professor Jianwei Chu at Jefferson Lab, and Professor Liu Mingxing, who will also give a talk later in Beijing, and Professor Chen Yongzong from University of Minnesota. My personal interaction with TD started in 2004. And in fact, I went to New York and to visit him, and he received me in his office. And Nagamiyana mentioned that it was Professor Yugawa's office. And under his encouragement, I became a Chanjiang visiting professor at Peking University. In fact, said in his Beijing Institute of Modern Physics building. And in 2006, at Professor Lee's 80th birthday, we established the Center for High-Energy Physics, and with TD as a director and myself as a managing associate director. And I remember very clearly that he told me that he will be responsible to get fundings, and he wrote personally to Premier Wing at that time, and to secure the funding for the center, and asked me to focus on physics. So this is some of the pictures that we took at that time, and Professor Lee had discussions with postdocs and students at the center. And we also, had yearly interactions. So he came twice a year, and then so he come to the center. He lives in campus of Peking University, so it's very close to the center. And so we had a lot of interactions. In 2009, I went to Shanghai Jiao Tong University. I was department chair in physics, and Professor Lee visited in May 2009. And he gave a very interesting talk. And I remember it was a big occasion, and something like 2,000 students attended the lectures in the big hall. So I reported to him that we're interested in doing dark matter experiment. And so he was very interested. So he personally wrote to the council member of State Council, Madame Liu Yandong, and asking her support for this new kind of dark matter experiment. And then around 2012, Shanghai Jiao Tong University proposed to establish a TD Lee Institute under the leadership of President Zhang Jie at that time. He was the first speaker here today. And it was charged with the initial phase of development of the institute starting in 2014. And TDLI was launched in 2016 at Professor Lee's 90th birthday. And we hired the first director, Frank Welchek, and after the consultation with Professor Lee. And so these are some of the photos shown here. You've probably seen it before, the TD Lee Institute. I will come back to what I've learned from TD over those years, roughly over a decade period. Now I'm going to turn on to the historical discovery of the broken parity. So in physics, it's taking as a fundamental axiom that the space is isotropic, means that when you rotate physics instrument or physical systems, we believe that physics is invariant under space rotation. And that is the basis for angular momentum conservation, a fundamental law of physics. And so therefore, it comes as no surprise that space should be symmetric under parity transformation. That is, the physics law should be under a position go to its negative position in the whole space the physics law should be invariant. Now, in the early spring of 1956, one of the most puzzling puzzles in particle physics was the theta tau decay problem. And these are two fundamental particles discovered in the scattering processes, and they both have the same mass, and their mass are exactly the same, but they appear to have a different parity. Parity is a behavior that when you do make that spatial reflection, whether the state is unchanged or changed by a minus sign. So that's called a parity. But it is puzzled that why these two particles, they have exactly the same mass, but they have opposite parity. And so in April of 1956, in the Rochester conference, there were many proposals, and one of which is the parity doublets, and the other is parity violations. But as the famous physicist Wolfgang Pauli said, if you just propose a theory to explain the data, but without any new test, it's a theory not even wrong. Okay, so the key point is not to come up with some idea that why the theta tau puzzle is like that. The key thing is actually to how to test whatever idea you have. So a breakthrough happened in hyperon beta decay, or hyperon weak decay. So hyperon is kind of a particle that produced when you have a pion scattered in a proton. And if you look at the plane formed by the beam and the lambda, and then the final lambda will decay into a proton again, plus another outgoing pions. And so if you focus on this outgoing pion, and relative to the position of this plane formed by the beam and lambda, and Professor Lee realized that if parity is not conserved, then the outgoing pi minus will have preferred direction relative to the plane. In other words, it could be upper the plane or below the plane, but if parity is violated, then you should see different number of events going the upper and lower plane. And so this is dictated by the so-called pseudoscalar, which is the product of the incoming pion and lambda momentum. So that defines the plane. And then the outgoing pion is the K out, and which is the projection along that plane. And that projection will be different if a parity is violated. So Professor Lee discussed this idea with the famous experimentalist Jack Sternberg, who later also won the Nobel Prize in the second half of the April, just after Rochester conference. But the data at that time was too scarce, okay? So in other words, there's not enough data to tell there is an asymmetry. Next thing we know is that in June 22nd of 1956, and a historical paper was written by Professor Lee and C.N. Yang, and they suggested testing parity in experiment. And this paper has an extremely short abstract, only 2 sentences. It says the question of parity violation, beta decay, and in hyperon and meson decays is examined. Possible experiments are suggested, which might test parity conservation in these interactions. Probably the shortest abstract in Nobel Prize winning papers. They pointed out at that time there's no experiment has any sensitivity to parity violations. And to do that, you have to measure pseudoscalars. Either you have a spin projected along the direction of momentum, or you just have 3 momentums making this the mixed product. And they proposed the 3 experiments, one of which is the nuclear beta decay, where you have a polarized nucleus with a fixed spin. Then measures some outgoing momentum, which in this case is the electron. And then you have in the hyperon beta decay, I just explained to you that you have the incoming outgoing pion and then laminar momentum. That's three momentum forms a product which tests parity. And also similarly in the pion cascading, you decay into muon and electrons, and so you can look at the three vector product. And of course that only a few months after this paper was published, the experiment data already came in to show that the parity indeed was violated. And the first is by Madame Wu, and in cobalt 60 beta decay, you can see the data clearly shows there's a symmetry. And same thing happened in the pion decay into muon and subsequently into electron. And you can see this oscillation here. This oscillation is the behavior of the parity violation. Now, the original experiment motivated Professor Lee's consideration of the parity violation signal is this the lambda decay. And now you can see that roughly a year, after this, October 1957, and you can see that finally you can see the number of pions going upper and lower plane, and they're different. And in the red circle, you can see that the ratio is not 1. And Jack Steinberg, as I mentioned, he also won the Nobel Prize later. And that, of course, led to the 1957 Nobel Prize in physics. And it's now actually the textbook material. I think every physics undergraduate and graduate student would know about this. And so here I will quote the reaction from one of the most famous physicists as well, Wolfgang Pauli. And so he received an article from Professor Li and Yang, and arguing parity may not always be conserved. And Pauli thought the very suggestion was rubbish. Of course, that Pauli always used very extreme words to describe, being very implied. Okay. So in fact, he wrote to his assistant, Weisskopf, at that time was already a very senior professor at MIT. In 1957, in January 17, 1957, that he was ready to bet a very high sum that those experiments would fail. And I don't know how much money he had at that time. What is a very high sum, but the answer is very clear. He would lose because the first paper came out was January 15th. So at that time, of course, we don't have emails, and so it takes time for people to know the news. And this is 2 days after the experimental verification. And so after learning that parity is indeed violated, and he said, "I can't believe God is a weak left-hander." That was his exclamation. So now I'm going to come to talk about what are the, significance, what are the importance that the parity is violated. And so I'm going to using Pauli's comment as a starting point to talk about why that's important. So God has two hands, and so let me explain the origin of this. In 1925, Goodschmidt and William Baker proposed that the electron has an intrinsic spin 1/2, so with two possible projections up and down. And then in 1927, although Pauli initially strongly objected to the idea of a spin, but he then became famous by introducing the Pauli spin matrices, and every undergraduate learning quantum mechanics should know this. And then a year after, Dirac discovered a relativistic equation for a spin half particle. And then you can define what's called a left and right-handed fermions. So I'm sorry, I forgot psi here. So this is a projection of 1 minus gamma 5. Will give you a left-handed fermion, and right-handed fermion will be 1 plus gamma 5. And those are called the chirality, okay, or handedness. Now, once you have two hands, on the two hands, the electrons and protons, all these matter particles, quarks, they all have two hands. And these two hands, they can wrestling with each other. And so you have a left hand, a right hand that wrestle, and that produces what's called a Dirac mass. I think this discovery is not without, a dispute, because the discovery of the Dirac mass probably is much earlier than Dirac, because according to a Chinese famous novelist, Jing Yong, in this Kondo Hero, the first person who invented wrestling between left and right hand is actually Zhou Butong. That's in the 12th century AD in Song Dynasty. And so I think probably we maybe should have called it Zhou and Dirac mass. But in any case, that let's think about what should be the size of the Dirac mass. If all interactions conserve the parity, meaning that all hands are equal, then the only scale of the mass must come from the Newton's constant of gravity, because no other interaction have dimension for couplings. And so therefore, all particles should have masses on the order of square of h bar c divided by Newton constant. So that's the Planck mass. So therefore, all particles should have a mass around the 10 to the 19th GeV. On the other hand, Li and Yang tell us that two hands are not equal, and the parities are broken. That means that two hands are not symmetric. If they're not symmetric, they can't really wrestling with each other. And so our conclusion is that all these particles should have mass 0 instead of Planck mass. But in the real world, what happened? In the real world, we have so-called Higgs mechanism. And we have a spontaneous breaking of this asymmetry between two hands that will generate a Dirac mass on the order of 100 GeV. Now, in some sense, that the spontaneous symmetry breaking of the vacuum means that the vacuum provides a lot of free hands, and so therefore you now can make a mass. Now, neutrinos actually is a very special particle among the, all the, matter particles. A neutrino god not only is a left-hander, which you call the new left, but it seems that have no right hand at all. So on the Christmas day of last year, I took this photo in Fort Lauderdale, Florida. You can see this could be a representation of a god without right hand. Now, can you have a mass with one hand? The answer is yes. If you have a charged neutral particle, entirely neutral, then the learning brother of Professor Li, Ito Majorana, introduced a mass with just one hand, which we call the Majorana mass. So suppose you have a left-handed neutrino, then you can have then a mass term look like this if the neutrino is charge neutral. But unfortunately, in the standard model, the neutrinos are not neutral because they have a weak interaction charge. So therefore, the Majorana mass is equal to 0, even though you have the opportunity to have it. So in the standard model of physics, the neutrino mass does not actually exist. So any non-zero neutrino mass would be beyond the standard model of physics. On the other hand, that we know that the neutrinos seem to have some mass. So the question is that how that happened, okay? It appears that the God has a hidden right hand. So if God has a hidden right hand, which does not have any standard model charge, and then it would have a Majorana mass. So the right hand can interact with itself. Then the only possible guess for this right-handed mass is again like what I said earlier about Dirac mass. It has to be something of order of Planck scale, the 10 to the 19th GeV. So therefore, this is an extremely large mass, so that two right hands you see wrestling each other, it was extremely large strength. But if you have a left hand and you have a right hand, the left to right could produce a Dirac mass, and the right hand can produce a Majorana mass. Then you have a neutrino mass matrix. And when you diagonalize this matrix, you can produce a small neutrino mass, which is basically the Dirac mass squared divided by the Majorana mass. Now, if a Dirac mass is in the order of 100 GeV, as I said before, if somehow the Majorana mass is the 10 to the 16 GeV, then we arrive at a conclusion that neutrinos have a mass about 1 millielectron volts. This is just the right scale. And so you can see that if I have the Majorana mass bigger, my the light neutrino will have a mass smaller. So therefore, this people call the seesaw mechanism. So one side gets higher, the other side gets lower, and that's a seesaw. Now, neutrino mass mixing and mass ordering is the frontier science problem, and China is making the leading contribution in this field. And studying a neutrino mass is probing physics at the 10 to the 16 to 19th GeV. And this is also corresponding to a temperature when the universe is extremely hot in a very early stage. So we heard the Dai experiment made historical contributions to neutrino mass mixing, but the upcoming Juno experiment will also tell us that what are the mass orderings and what are the three different neutrinos on how they order their mass. In this historical 1956 paper, and Professor Li and Yang also wrote, one has therefore, and after discuss about a parity violation, they said one has therefore at present no experimental proof of invariance on charge conjugation of weak interactions. Now, charge conjugation is positive to negative charges, and also called a matter-antimatter symmetry. And they discovered that in the simplest physical theories, the broken parity also lead to the charge conjugation violations. So let's look at the matter and antimatter symmetry. So here you have a proton in the center, you have electrons that forms an hydrogen. However, if you have an antiproton in the middle, you have a positron flowing around. That's an anti-hydrogen, and that's an antimatter. So if parity is violated, it is quite possible that charge conjugation or matter-antimatter symmetry is violated. And this is extremely good news, because if matter and antimatter were totally symmetric, the universe today will be just filled with radiations. There will be no matter, no us. We wouldn't exist. So our very existence owes to the breaking of charge symmetry and parity symmetry, which led to a very tiny matter-antimatter asymmetry, which is it's about 1 part in 10 billion. So when the universe was hot, if you have a 10 billion matter particles, 10 billion antimatter particles, or 10 billion and 1, so they all annihilated except the one is left, and that's us. So without a symmetry, we won't be here. So we're the survivors of the biggest annihilation in the cosmic history. Now, I've talked about the effects of parity violation in microscopic world and also in the very early history of the universe. However, parity violation is not that esoteric, and we can see in our naked eyes. And we can see the parity violation on Earth. We can also see parity violations in the sky. Now, so let me start with the parity violation on Earth. almost all animals, including human beings, human being is by definition one of the animals, appear to be left or right symmetric, right? So all of us looks like symmetric, but there is a fundamental asymmetry. For example, our heart is growing on the left side, and in principle, we should have half of people on the left and half of people on the right side with the heart. And most of people are right-handed, and then maybe those are two related, okay? And then if you look at the brain anatomy, and then the brain has no left or right symmetry, obviously. And so therefore, this was actually traced to a phenomenon called the chirality of molecules. So if you have a molecule with a carbon with bind to 4 different other molecules, and it appears that when you have 4 strands, you can form a left-handed and a right-handed molecules. And in particular, amino acid, aniline, occurs in 2 forms. They're called enantiomer, or I don't know how to pronounce this, enantiomers. So you have the left-hand side aniline, and you have also the right side aniline, or one is called L, another called D. And it was discovered in biology. In fact, even in the 19th century, we always discovered that our bodies are full of chiral structures. It's made of one chirality, not the other. So if you look at the DNAs or amino acids or peptide, and they all have, they're not an equal mixture of these things, left and right. They have only one particular kinds that present, either left or right. So our body is actually chiral. That may explain that why our heart is growing on the left side, not in the middle. And so that's a very interesting phenomenon. Because of that, this left or right asymmetry, if you look at certain medicines, and they have exactly the same molecular composition, but is a left or right image of each other, they have totally different effects on our body. The left side is a painkiller, but if you look at the mirror image, this is an anti-cough agent, actually. So they're have entirely different effects. Now, this left or right asymmetry may be due to weak parity violations. But of course, weak parity violation is much too small compared to electromagnetism. But recently, some Japanese physicists, when they do molecular structure calculations, they found that the weak interaction energy gets amplified by hundreds of times. So therefore, that the 2 different kind of molecule may have different energy, and so therefore, somehow one form is preferred than the other when in the biology evolution. Now, because of this chirality, we have a chemical or drug production problem. Because if you try to make a medication in a laboratory, usually that a mixture is obtained, and half is one kind, one symmetry, and then the other half is the other symmetry. So the synthesis is automatically symmetric. But in biological evolution, only one particular kind passes from one generation to another. And so that produced a big problem for drug production. And in fact, there's an infamous example that there was a defective vaccine produced in 1957 that's used to cure nausea and insomnia in pregnant women. And it turns out that when this vaccine was used, that they will produce a defective child. And eventually it was traced to the fact that they have the different molecular arrangement have different mirror symmetries that causes this problem. Now we heard Professor Noori, who was the director of Riken, who is actually a good friend of Professor Lee, and he won the Nobel Prize in 2001 to discover chemical processes which you can only produce one kind of molecule, not the other. And so this is called inertial selective hydrogeneration. That's his work. It's related to selectivity in a jet production, and also the sharpless was for the oxidation process. Okay, so finally I come to the parity violation in the sky. Now the universe, as we see it at a large scale, is homogeneous and isotropic, but locally we have fluctuations. So we can define the density locally and then look at its fluctuation, which is called a delta. Then we can form endpoint correlation functions, and all its fluctuations, densities at different points, we average over the universe. And to test the parity in the sky, we need 3 independent vectors, just like in the meson decay. We need a K1, K2, K3. And so that needs 4-point correlation functions because the space is homogeneous. And so therefore you can shift one of the points. In 2023, these 3 gentlemen published a paper that they think that they can test the formation of the galaxies, whether there is a parity violation or not. So it turns out the Sloan Digital Sky Survey 3, there's a BOSS collaboration called Barying Oscillation Spectroscopic Survey. They took a lot of data and mapped the distribution of the luminous red galaxies, LRGs. You can see that each of these dots on the right-hand side represents a galaxy. And there are lots of them. So they're divided in 2 categories. One they call the low Z, there's 280,000 galaxies. And the other CMAS has 803,000 galaxies. And so these 3 gentlemen made analysis whether the galaxy distribution in the universe is left or right symmetric or asymmetric. So their conclusion is that for the CMAS data, at the sigma of 7.1 level, there's a left-right asymmetry. And the other data set will have 3.1 sigma asymmetry. And then a postdoc, Phil Cox, and did the same analysis and found the same conclusion. And this study suggests that there's a detection of asymmetry at a probability of 99.6%. By the way, Phil Cox, guess where he is. He's a postdoc at Columbia University. So let me just make some final comments. I hope you agree with me that if parity were not broken, the universe as we know today probably does not exist. So therefore, we love this biased but infinitely more accommodating universe. Einstein had a famous statement about nature that he said, subtle is the Lord, but malicious he is not. So that, shown that the nature has extremely interesting subtleties. I would paraphrase, but it was a more positive comments. That is, Professor Lee was young and helped us to learn that God is biased, but towards the benefit of human being. And without this bias, we won't be here. And as I said earlier, that I have interacted with Professor Lee for over a decade. And so this is what I learned from him. Professor Lee is a true physicist of most enthusiastic kind and kept the interest until his last days. Most of the Nobel Prize winners, after win Nobel Prize, they're going around, flying first class, drink expensive wine, and they don't do science anymore. But Professor Lee does, He was still writing papers when he's 80. And he's the most generous soul. And he gave lectures in Beijing, Caspar students, and Drengen Foundation. He lent his relentless support for hydrogen physics in China. We heard many examples in early talks. And he has a humorous personality and great storyteller. And that's something I cannot expand here due to limitation of time. And you know, we had dinners together and drink a lot of, you know, wines and beers, and he would keep talking about interesting stuff. And most importantly, what I learned from him is no detail is too small, and he always with attention to all the, you know, details. It's very important. So that's the end of my talk, and so final slide show my appreciations for people who helped me with this talk, and also for facilitating my interactions with Professor Lee for more than a decade. That's the end of my talk. Thank you very much.
Okay. Thank you very much, Shandong. It's a very nice talk indeed. Okay, due to the very short time, I think we won't ask questions anymore. Okay, let's invite the next speaker, Professor Wu Liang.
Okay, thanks the organizer to invite me to have this opportunity to express. Okay, my memories to Professor T.G. Lee. So my talk contains two parts. One is about Professor T.G. Lee and his ties to the Institute of Theoretical Physics, Chinese Academy of Science, and also his impact on me. And then I'll talk about the spontaneous CP violation moderated by the T.G. Lee. So after I hear the passing of Professor T.G. Lee, I just wrote this condolence. Okay, so I try to English maybe it's hard to express. So I asked the DeepSeek translator into English, but I prefer to speak in Chinese now. So 今些李政道先生去世的消息，这个深感悲痛。李政道先生是享誉世界的理论物理学家，诺贝尔物理学奖获得者。他和杨振宁先生一起提出的宇称不守恒理论是历史物理学的基础，影响了物理学发展的方方面面。他一生心系中国科学技术和高等教育的发展，以及中美合作交流、中国高能物理的起步、博士后制度的建立、国家自主科学基金的设立、中国高等科技中心的成立，以及中美联合培养物理类研究生计划卡斯比亚和中美科技合作交流，无一不是得益于李先生的着力推动。在我担任中国科学院理论物理研究所所长期间，曾多次和李先生交流他倡导的自由宽松和开放交流的学术氛围，在理论物理研究所的国际化交流合作和前沿交叉研究起到了积极的重要影响。他一直关心和支持理论物理所的发展。2008年，理论物理所成立30周年所庆活动之际，李先生特意从美国赶回来参加，并且提示理论所用战赛创新的最前沿。我本人也有幸得到李政道先生的强烈推荐，于1987年赴德国开展博士后研究，德国多特蒙德大学。1997年回国后，与先生接触和交流机会变得更多。先生每年都会回来亲自推动中国的科教事业发展和国际合作交流。然而，2011，我原来写的是2011年，后来我跟王传林老师确认一下，是2010年春，我和戴维的格罗斯教授跟李先生一起共进早餐，竟成为我与先生见面的最后一次。之后，尽管先生由于身体的原因无法亲自回来，但他仍然一直关心中国科教事业的发展。先生在现代物理学和中国科教事业发展做出的杰出贡献，将永载史册。我写了一个简单的一个小诗，叫“正通中美促交流，道法自然破宇称，离岛而今满天下，科学艺术均一人”。这个我让这个 DeepSeek 翻译成这个，简单让他翻译这是个，他是第一个翻译。我后来说，我用中文说， 请将这首诗翻译成英文，并考虑其文学性、艺术性和科学性。那么它的翻译就是 Promoting exchange between China and the U.S., mastering nature's law to set parity hold. Now your legs spreads far and wide. In science and art, you stand alone, a luminary bold. Professor 郑道理 will live on forever in our memory. Okay, so so now his ties to Institute of Theoretical Physics, Chinese Academy of Science, and we see the CCAS was officially inaugurated affiliated to Institute of Theoretical Physics, Chinese Academy of Science in 1980. So you see this small buildings, and also for the world laboratories. So I'm lucky. So in the inauguration, I will stand here. So you see this is General Counsel of Institute of Theoretical Physics, Professor Zhao Enguan, and Professor T.G. Li and ZZK, and you see Ye Minghan, Gan Zhizhao, 这个还有一个是北大校长，我们这个陈嘉尔。这个是这个World Library inauguration 的是一些照片。Are some photos, and also Professor T.G. with Professor Pan Wanwu and Professor K.C. Zhou, the founding director, Professor Pan, and also Professor Zhou's former president of Chinese Academy of Science and a former director of Institute of Theoretical Physics. And so after Professor T.D. recommended to as postdoctor in Germany, so I first met him in 1992 at the summer school on quantitative particle physics at the Cagissi in France. And he gave a talk about the history of weak interactions. From his talk, I was first know that the weak gauge boson was initially motivated by TD and Xiang Yang. So I come back to the Institute of Theoretical Physics. So I become the deputy director, and I organized the first series forum on frontiers of science. Actually, I invited TD as the chairman. He accepted, and the first talk by Professor Zhou in 2003 in April. And I become the director of ITP, so I come to TD's office at CCAST and to ask his suggestions and how CCAST and ITP work together, especially for international cooperation and exchange. And TD actually, from that time, he always sent me his season's greetings, drawn by himself. Yeah, for example, so I received his season's greetings for 2008. Her job is the season's greetings. Okay. And so in 2008, the ITP, celebrated for the 30th anniversary, I invited TD to give some words and invite him to come. And yeah, he gave strong support. He not only write some, his inscription and the Institute of Theoretical Physics will always stand at the forefront of innovation, but also he come directly to attend this anniversary of ITP. And together with Xiang Yang, and you can see this is very important photos we kept. Yeah. And then to celebrate Professor Zhou's 80th birthday, I prepared the select papers for Professor K.C. Zhou, and I wrote to TD again to ask him to write the foreword. So TD actually gave strong support to write this very long foreword to this. And then TD, because for the celebration was in May 2009, TD's schedule is very busy. He couldn't come, and he told me that he'll come later in June 2009. And then I invited him to present talk about the Forum on Frontiers of Science. He was chairman in the first time, yeah. And Professor Zhou come to hear this, his talk. He talked about the neutrino physics. And to go to front, yeah. It's very happy together, yeah. See. Okay, so now we come to the CP symmetry and the symmetry broken. We know the CP symmetry reflect the basic symmetry between particles and antiparticles, and also the mirror reflection of left-handed and right-handed particles. It concerns the fundamental symmetry of space-time and matter. The CP symmetry and its violation have long been at the forefront of the exploration of the fundamental laws of nature in particle physics up to now. So we might just see some important progresses after the discovery of parity variation. So after the paper by TD and Xiang Yang, so then there's the theory about the V mass A theory, so assume the maximum parity violation, and also some hypothesis of massless neutrino with the maximum parity violation. And then in the 1960s, now we have this PCAC theorem and the standard model, electroweak, and then discovery of indirect CP violation in count decay, and then the quark model and quantum chromodynamics, so in 1960s, 70s. And after that one, the people explore the ground unified field theories, SU5 or SU10 and so on. And to the 1980s, the discovery of W-engaged bosons. As I said, it was first initially by the TD. And he told me that he just gave the ideas. It's just qualitative, it's not quantitative. Okay. And then we have this massive neutrino, and also the dark energy in 1990s. In the 2000, the new centuries, we have the observation of direct CP violation in B decays and K decays. And also now, the 2010s, the discovery of Higgs boson, discovery of gravitational wave. Okay, here's TD, Xiang Yang, and Cronin, and Vichy for indirect CP violation, and also for direct CP violation in the standard model. And Kobayashi Masukawa. So anyway, so the experiment from B decays and also from the K decays, okay, in K decays. So we have experiment and the theory. And especially for the prediction of direct CP violation in K decays, should simultaneously understand the data half rule, the isothermic selection laws. And with the principle of CP symmetries, the matter and antimatter should be the same in the old universe. But we now, in the current, we can only observe the matter without antimatter in the universe. That means the CP symmetry should be broken down during the erosion of universe. And then we will ask, although the CP violation has been observed in the standard model from B decay and K decay, but why we need the CP violation beyond the standard model? Because CP violation is a necessary condition for explaining antimatter asymmetry in the universe, where the CP violation within the standard model is not enough to account for the observed antimatter asymmetry in the universe. And also CP violation in the standard model put by hand, okay, through complex Yukawa couplings. Its origin is still unknown. Okay, so it necessitates for the existence of a new source of CP violation. So this made the origin of CP violation as one of the unsolved mystery in the standard model of particle physics. So then we come to the issue, important issue, the origin of particle violation and CP violation. And this was by Professor T.D. Lee. In the same year, when Kobayashi Masukawa introduced the CP violation in standard model by the complex quark coupling, T.D. suggested a spontaneous CP violation. Okay. He stated the scalars are responsible to CP violation. So CP violation originates from the vacuum. So actually, this is the basic idea by TD, also for the strong interaction, okay, for spontaneous dynamic symmetry broken of quantum chromodynamics to get the mass of a dynamic quark of mass to understand the mass of proton and the neutron. Okay. And after that one, there's the Mohapatra suggests the left-right symmetric model to understand the spontaneous CP violation with the one Higgs bidoublet. But this model actually now is excluded from Coundic and from Bolton-Masson case. So here is the original paper by TD, a theory of spontaneous T violation. Because CPT conserved, T violation means CP violation. Okay. So see, what I see after TD's idea of spontaneous CP violation, there's a lot of papers started spontaneous CP violation. Here I just pick up some interesting papers. First by Weinberg. He suggests a 3 Higgs doublet model with discrete symmetries. That means CP violation arises only from the Higgs potential. But this model is actually ruled out by the B2S gamma decay and also electron dipole moment of neutron. And after that one, and Glasser and Weinberg suggest a natural flavor neutron flavor conservation hypothesis with discrete symmetry. With this hypothesis, so in 2 Higgs doublet model, which is called type 1, type 2, 2 Higgs doublet model, there's no CP violation. And then in 1978, the George want to understand the strong CP problem and also biogenesis. He suggests a soft CP broken in the 2 Higgs doublet model. And up to the 1987, after 10 years after Glasser, Weinberg, and Liu and Wolfenstein suggested the approximate discrete symmetry beyond the natural flavor conservation in the 2 Higgs doublet model. So there's small flavor changing neutron current, which understands the superweak interaction of CP violation, initially motivated by Wolfenstein himself. So up to 1993, so Hall and Weinberg, actually they gave up their natural flavor conservation, the neutron flavor conservation hypothesis. This by Glasser and Weinberg. Because this hypothesis actually makes spontaneous CP violation almost no great progresses. So then Hall and Weinberg suggest a approximate flavor symmetry to understand the superweak type CP violation in 2 Higgs doublet model. So then after that one, and Lincoln Wolfenstein invited me to visit the Carnegie Mellon to work with him about CP violation. So I studied all 2 Higgs doublet model, meta Higgs doublet model, and then found they are not so natural flavor conservation hypothesis not necessary. So then I proposed the 2 Higgs doublet model with approximate U1 family symmetry with a spontaneous CP violation, which called the type 3 2 Higgs doublet model. So then we found the CP violation originated from a single relative phase of vacuum excitation values with spontaneous CP violation. So in this model, we have 4 types of CP violation after symmetry broken, which covers all the sources of CP violation. So when we can derive the Kobayashi-Maskawa phase in the CKM matrix of standard model. Second, there's new source of CP violation with the charged Higgs interactions. And then we'll also have the flavor changing neutron current with the neutron Higgs, which understands superweak type CP violation. And there's another one is scalar, pseudo-scalar mixing CP violations. Okay, so then we published 2 papers. But with these publications, I actually wrote a very long paper, a model of CP violation, about 8 pages, try to convince the people. Before these papers, I wrote 5 papers to convince people this general 2 Higgs doublet model with rich CP violation source is consistent. But nobody actually believed me. So eventually, Lincoln Wolfenstein asked me to his office to discuss details about this model. So I first convinced Lincoln Wolfenstein, and then I eventually accepted, actually. It takes me almost 1 year for this fighting. Yeah. And then we can discuss the origin both P violation, parity violation, CP violation, spontaneous in the left-right symmetrical model, for example. And so we introduce the right-handed neutrinos, of course. And then this contact with 2 Higgs bidoublets, not only one Higgs bidoublet by Mohabbat party is excluded, but if there's 2 Higgs bidoublets, then there's a rich CP violation sources. It's consistent, and also has more phenomena. Time is okay. Recently, so okay, I have no time to follow more details. So recently, so I developed a general theory of the standard model and the revelations of the dark side of the universe, which actually the maximum parity violation plays a very important role. So I just have this abstract. So just within the gravitational quantum field theory developed by myself, so we construct a general theory of standard model based only on the intrinsic properties of leptons and quarks, and also principal gauge symmetry, without introducing new content of basic constant. We only have the leptons, quarks in the standard model. And then we can unify the standard models of particle physics and cosmology. So this model not only describes the 4 fundamental interactions, electromagnetic, weak, strong, and gravitational, and also the Higgs scalar interactions, but also predict more than 6 new interactions. Okay? So these interactions is made from the maximum parity violation. So that's why I call it the interactions called the spin, chirality boosted spin, carrier conformal spin, and scaling gauge and scaling scalar interactions. So then we will find this factor gauge boson corresponding to this chirality boosted spin force is a massive stable particles. So we call it a dark graviton, which can serve as the candidate for the dark matter. Okay. And for the scaling scalar bosons, which can provide the sources of the primordial cosmic energy and the dark energy to understand the phenomena of early universe inflation and the current accelerated expansion of the universe. Okay. So most important for this gravitational quantum field theory, we should start from the basic constant of matter, leptons, quarks, but we should not start from geometry, like Einstein in the general relativities. Okay. So then we can understand both standard model in particle physics and standard model in cosmology with cold dark matter and like cosmological constant and so on. Yeah, I just show explicitly. It's very important with leptons and quarks, left-handed, right-handed. The chirality property is very important. That we can show in the standard model actually there's a carrier duality symmetry, this Z2 symmetry. So it's a left-handed, right-handed, you can exchange it. So that should be equivalent treated. So then we found in the standard model, within the standard model, okay, except the normal gauge symmetries, 1, 2, 3, so electromagnetic and weak and the strong interactions for these 3 groups. And then you will find there's additional symmetries. I call the conformal inhomogeneous spin gauge symmetry. So this is for spin symmetry. This is a chirality boosted spin, like is like a translational symmetry in coordinate spacetime. But this is in the spin. In the spin related, I call the spin related graph gauge spacetime, and also it's conformal, carrier conformal scaling symmetries. So with these symmetries, okay, within standard model, you just put this symmetry as the gauge symmetry, reconstruct the standard model, and you can write down these actions, okay? And then eventually you can, with the gauge invariance principle with covariant derivatives with these gauge symmetries. It's very simple. So here you have some group generators for the spin symmetry, and the chiral boost spin, and the chiral conformal spin, okay, corresponding to each gauge symmetry corresponding to the gauge field. So this for the electromagnetic induction and weak induction, strain induction. Then we have strain as a spin gauge symmetry, spin gauge forces. Okay, then you have the chirality boost spin gauge symmetry. Okay, so it's W mu A. This is the factor bosons. This boson we found is decoupled from interactions with leptons, quarks. It becomes stable surface as I call the dark graviton as dark matter. And you can also have this scalar. Naturally, we have to introduce the scalars to Kepler scaling invariance. So this provides the promoter energy for inflation and dark energy for accelerated expansions. Okay. And within the gravitational quantum theory, we can extend this general standard model to the hyper-unified field theory. So to unify all elemental particles, leptons, quarks, and forces. So with this long articles, papers. Eventually, in these models, we should understand why the leptons and the quarks are chiral females with maximum parity violation. Because in these unified models, we need to introduce the mirror leptons and quarks. That's really understand the spontaneous P parity and the CP violation, and also will involve the high dimensional space. And okay, thank you.
Professor Luo Mingxin, please. Okay.
We are running late. I try to make sure that everybody gets his or her lunch on time. As Xiangdong mentioned, that I'm one of those Cuspia students who study particle physics. So I'm charged by the committee to pay tribute to Professor Li for his tremendous contributions to quantum field theories. Instead of to give a full review of Professor Li's contribution, I mainly concentrate on three papers, seminal papers by Professor Li. The Li model, which dealt with the ultraviolet divergence non-perturbatively, and the KLN theorem, which dealt with infrared divergence, and which has a tremendous influence on today's physics, and also the quantization of vector fields, which we will find out that in the early 60s, it's highly non-trivial to renormalize this field. And I'll conclude with a personal note. First, the Li model. You see, the infinities has plagued the quantum field theories since its early days. In their first papers on quantum field theory by Heisenberg and Pauli, they anticipated the infinities in theory. So at that time, people thought that we can ignore that. There was the saying that because it's infinity, that cannot be observed. So for something like 15 or 16 years, this thing set dominant. However, after the Second World War, a lot of progress in experiments and in theory, people realized that infinities they are not, they could be observed. So, following the discovery by Lamb and Raby, Feynman, Schwinger, Tomonaga, and Dyson sketched out a proof that to all orders of perturbation theory, all infinities can be absorbed into the definitions of fields, coupling constants, and mass in QED theory. This is the so-called the renormalization scheme. See, in the renormalization theory of QED, calculations of anomalous magnetic moment of electron and the Lamb shifts in the hydrogen atom experiment can be measured precisely and be predicted. They match each other very well. As one of the most accurately verified predictions in the history of physics, the QED prediction of the anomalous magnetic moment of electron agrees with the experimental value to more than 10 significant figures. So then why the Lie model? You see, all those calculations are done within the framework of perturbation theory. So people would very much like to get an understanding of the renormalization book without the use of perturbation theory. So Professor Lie devised a very elegant, simple model to show that renormalization theory is not an artifice of perturbation theory. So as Pauli and Callan said, this model is simple enough to allow a more or less explicit solution and complicated enough to contain many features characteristic of more realistic theories. Actually, Pauli spent quite a bit of his time into the Lie model. In the same year, 1954, when Lie published his paper, Pauli actually wrote a very lengthy letter. And he began with it. He said, "Dear Lie, it's already some time that I started to study your paper seriously. Days become weeks, weeks to months, and my life, Lie model is still increasing, a proof of its importance." And somebody, quite a few years ago, somebody noted that later might have been the origin of the term ghost. Actually, the Heisenberg was also fascinated by the Lie model, and on his 70th birthday ceremony, he gave quite a lengthy review of the Lie model and its relation with his unification theories. I skipped the details here. You see, and if somebody wish, they can get this page. Heisenberg's writer for the talk on the net. So now let's go back to the Lie model. The model is quite simple. It has two heavy neutral spinless fermions, V and N, and a light neutral boson, theta. No kinetic energies for V and N. So there is no recoil effects. The only interactions in the theory are the ones in which V converts to N plus theta and vice versa. So the model is exactly soluble in sectors of finite number of particles due to two simple conservation laws. The model can also be renormalized by perturbation theory. In general, this is quite beautiful and elegant theory, but there is one defect in the theory, because in general we can prove that the coupling constant and the normalization constant is between 0 and 1. However, if we use perturbation theories, the normalized coupling constant and the bare one, they differ by a sign. There's this minus sign. He said that this shows that the result of coupling constant renormalization in this problem cannot be realized by any limiting process if G is restricted to be on the real axis. So, but however, if we give a pure imaginary G0, the Hamiltonian is then non-emission. So Pauli and Callan pointed out that in 1955 that the introduction of an indefinite metric, so that could resolve the above conflict of Z. However, the S matrix of the Lie model might not have been unitary in this case. With the help of Callan, Weinberg, actually in his first published paper in 1956, proved that there are states in the Lie model whose energies are complex. We know that for states with negative performance are quite common in gauge field theory. For example, in QED, its time-like polarization is also of negative norm, but the gauge symmetry protected the unitarity of the S matrix by the inclusion of an physical photon with longitudinal polarization. But here we do not have gauge theory. However, the things make a twist in the late 90s. Bender discovered that the importance of parity and time symmetry in non-Hermitian quantum field theory. In 2005, Bern and al. Proved that the Lie model is an acceptable unitary field theory, and by proper definition of inner product. And later, Bender was recognized by the Heinemann Prize for his contribution for this problem. So now we come to the KLN theorem. This is quite a profoundly significant paper. And it dealt with the perturbation theory of degenerate states. It's foundational to the framework of perturbative gauge theory, because we have multitude of massless particles in the theory. Its true impact unfolds only with passage of time. Let's go back to simple quantum mechanics. When degeneracy emerges within a quantum mechanical system, it can give rise to singularities tied to the degeneracy. Let's look at the S matrix here. The second term, in the second term, the denominator. When the states are degenerate, then we have another divergence. So it is quite typical when we deal with massless gauge theories. We have this kind of things, such as QCD and QED. So nowadays, they are also known as soft and collinear singularities. Ensuring the cancellation of such a singularity in theoretical predictions is instrumental in physics program at high energy physics. So the cancellation of singularities to all orders in perturbation theory can be done in an extremely elegant way, thanks to unitarity. We note that in the transition property is a product of the S matrix, and for degenerate configurations, we will see that the infinities can be cancelled out by the inclusive transition probability. The proof is quite simple and elegant. From the unitary condition, the off-diagonal piece of U dagger and U is equal to 0. So if we sum up all the degenerate states, then we can make sure that all the divergences they cancel out. So in the end, we get a final result. So as we can see here, that in this paper, it provided a foundation for the jet theory. This problem of cancellation, this problem of cancellation of degeneracy singularity is not only of perturbative interest. It closely connects to the fundamental questions of confinement. One may well ask that, how does conserved charge transport from quark-gluon degree of freedom to hadron degree of freedom? And here, the KLRN work is the most important motivation for the recent studies in energy-energy correlations. And as we see on the right of this transparency, that the certain collaboration measured in the energy correlation is quite a beautiful curve, and the perturbative prediction is on the right of the figure, and which is without the KLRN theorem, this kind of calculation cannot be done. Finally, I would the third paper I would to mention is how to quantize the vector fields. Nowadays, we know that the consistent theory for a unified gauging model of weak and electromagnetic interactions is the so-called Weinberg-Salam model. And it's self-consistent and it's remarkable. Actually, how to quantize theories like that is highly non-trivial in the early 60s. And Li and Yan proposed a pioneer construction of the quantization of massive vector fields. To make a long story short, basically they did two things here. They used the so-called canonical quantization procedure and introduced the so-called the Cassie term into the Lagrangian. And they found out that in the Cassie limit, the Cassie to zero limit, all terms in Feynman diagrams become relativistically covariant. The introduction of negative matrix at Cassie larger than zero, the program become renormalizable and covariant. And in this paper, we also a very peculiar term is a determinant, which is essentially a precursor to the Faddeev-Popov-Ghost contribution. And all those Feynman diagrams that are produced by the past-integral quantizations in the early 70s. So this is the scientific part for Professor Li's contribution in quantum field theory, which I'm talking today. And I'll finish with a personal note about Professor Li and the Zhejiang University. In 1943, Professor Li started his physics career as an undergraduate student at the Zhejiang University. So almost half a century later, in 1991, he founded the Zhejiang Institute of Modern Physics at ZJU and serving as the founding director until his last days. And my personal connection to Professor Li started with that. In 1983, I graduated from the ZJU and entered the University of Pennsylvania through the Cuspia program. And I met Professor Li the first time in 1984 when he came to Penn to deliver the first Primakov lecture. And I benefited tremendously when I was visiting the BNL in the summer of around the 90s. We had lunches almost every day, every working day for 2 weeks, that's usually. So maybe like Xiangdong said that I will talk about that some other time. So in 1994, I came back to the Zhejiang University, and I joined the Zhejiang Institute of Modern Physics, serving as a faculty member for more than a quarter of a century. So in 2017, I fly to San Francisco and see him the last time, to basically to report the situation in the Zhejiang Institute of Modern Physics, and also personally to say thank him again, maybe the last time. And I guess at that time both of us sort of aware of that. So as we can tell today, Professor Li is deeply missed, and his heritage will be cherished, and he will be remembered, honored, and by many of us. At least I deeply miss him now. Thank you.
Okay. Thank you very much, Li Xin. And also let's thank all the speakers in the morning sessions. I think before I formally close the morning session, 2 announcements. The afternoon session will start at 2 o'clock. And also for the lunch, you look at your ticket. Actually, the lunch will be in 2 restaurants, so you really read your ticket and see which restaurant you should go. Okay, thank you very much.
start. And in the first section, we have first that let's say increase from Columbia University. It's going to talk about physics from the center of activity in Professor CD. Please. Rather small, but his career and influence, which is his effect on my research and study CD, and that is using numerical methods. So I would begin by talking about the role in the beginning of latitude CD and the first 20 years where latitude CD is developed as a tool to understand this nuance, and then go on to talk about modern time now, and we're really using it quite successfully to make predictions from the standard model that involve the parsing one in an intrinsic way, where a real precise numerical control is needed of this non-primitive theory. And this is some current research if for certain basic as someone who very much fostered this particular direction in particle physics and energy physics. So the beginning, of course, we're talking about a particle representation of quantum mechanics, the relativistic field theory with a very strong coupling, the property that you go longer distances, the forces get stronger and stronger, and finally find the in hadrons. This is not something that is easily dealt with using chemistry. Really, new method is necessary. A method that I would say Ken Wilson invented in the early 60s. The picture on the right is just a lattice, in this case, would be a space-time lattice, but fourth dimension is needed, and using the variable to find on a lattice, the value of the variable is basically looking at the exponential of the QC Hamiltonian as if we were evolving a climate system in time, but without eyes. So we're working in Euclidean space, which is a bit unusual. Of course, the QC Hamiltonian is the QC Hamiltonian. We can learn a lot about across stated properties of QC if we can evaluate this. And there's a non-formulation where literally form find method using micro methods. So the this formula represents a expectation value of the operator of that number of states to be the rate exponential operator, which calculates many more operators, for example, getting a destroying Fritzman, where the time dependence depends on the time between two operators give you mass of the photon. And this is written as also written in age degrees of freedom, and have a billion by indeterminate here, a very large secret here that includes back action of the quarks on the quants. This is evaluated Monte Carlo importance sampling using hybrid microdynamics Langevin evolution, and we're integrating over a volume of 20 billion dimensions. So this is an enormous numerical problem, but one now that appears to be suited to the problem at hand. With this number of degrees of freedom and this scale problem, we can actually accurately calculate in some cases with 10% the consequences of the quarks and quants. So he was always focused on physics. He was not enjoyed mathematics. His desire was to be an nature, and he hadn't biases in terms of what you should do. He was enthusiastic about numerical methods from the earliest days of talking to him for PCs for electronic calculators. I believe I could recommend a hand calculator. And it was a tool of his there. And as I'm involved in more fancy tools became available, he was a person investigator of our grant economics. And the people in the grant department of energy sort of looking after him and wanted to get most out of his talent. Well, maybe he should have a better computer. And so suggested that they should provide him with a PD-11 computer, a very, very popular DEC machine. And he agreed to it. And I actually ended up doing a postdoc install it. And then I ended up using it a little bit more than it was certainly the enthusiasm of the people at the department. This is something he needed. They got started. Mr. Kurtzman from Zini experiment at Columbia. One of my built a simple hardware accelerator. We connected the PD-11. It allowed us to gauge multiplication faster than the machine itself. But we used a special purpose jet just becoming available and possible for an amateur to so this started a little activity at Columbia. TD found space for and was money for and encouraged very much using QC machines to solve that QC. So something you can currently do with an open computer, you can do it less space if the computer is designed for the purpose at hand. So this is a picture of an accelerator for PD-11 and a series of increasingly complex machines that achieve higher and higher performance and had more and more nodes. So this is a combination of friendly technology. You can buy these TCL technology chips. You could just wire together in a simple way, and they would do their calculation. You would wire them together to do. But also use computing because the size of was very homogeneous. You could have individual processors that could be assigned to specific regions of space-time, and then connect them together with wires and with covers removed from these machines. You can see there are a lot of wires making a connection. This is very straightforward parallel computing, and so for commercial application, we have a more complicated problem. Parallel computing becomes a challenge, but for us, it's really quite straightforward. It's something that TD certainly appreciated and encouraged. So in this period of time, we learned to do physics, principally finding temperature physics to be relatively difficult, about a billion. But main emphasis was developing technique. So this is about 1990. At that point, I think we became serious to remove the speaking collectively internationally of moving QCD forward by literally trying to address this methods were available. We could really work on interesting problems, but there were important things that were missing. So the original calculations were all done without loops. Fun diagrams were studied. We were effective in all kind of diagrams that works in initial state, propagating through the works in the final state, no virtual loop. So this is something that had to be fixed. And additional computing power is a very clever programming idea. Also, was the tendency to even the valence part of the problem, work on quarks that were quite a bit heavier than physical. How to use calculation theory to extrapolate from the physical region. This is certainly not a crazy thing to do. It's not very accurate. If you want to work with an extension, it's probably best to start with the extension good and try to go in that direction. You know, start with quantity quarks and extrapolate in the region doing this with so-called overlap translation, which solves this had essentially fifth dimension in our four-dimensional system that allows hierarchies to be treated properly. So we end up with a five-dimensional problem with two left and walls and hierarchies of leading exterior interactions of them left and right-handed walls. It's actually geometrically quite entertaining. Of course, that's a fraction and cost effective these walls by 10 copies of our four-dimensional lattice. This is a super algorithm was completely stable down to physical hardness. It works just fine. And it also allows the theory to create the theory has spiral symmetry at very short distances. So you can use the properties of spiral symmetry is when you normalize the theory just as well as to do physical low energy predictive theory. But then tackling the systematic errors of finite volume, finite lattice spacing, all have to make the lattice theory require a large number of sites. This is expensive. So very important part of the challenge that the theory has is that we need probably somewhere between a factor and a number computing power to include the Fermi determinant, make the volume twice as big, and because it's in four dimensions and the increase in cost, an extra factor 10 for our five-dimensional formulation, so all gets to be very expensive. At this point, the activity of designing our own computer became quite important, because now we could try to achieve this level of increased performance by taking a bit more money, something that TD was very good at. So with his special assistance, we were able to move on to much larger machines that involved perhaps 1,000 nodes, and this required new funding. It required support from the Brookhaven Research Center, which we heard earlier today from Shoji Nakamoto, was happily led by TD, who made this lattice research an important part of the mission. A significant part of it. Their main issue was main objective was experimental research. Having a little experimental research to the tune of $1 million or so was certainly something that TD had no trouble managing. On a larger scale, for the OUS community, TD and Frank Wilczek, a very successful case, Ray Orbach, who was director of science at the DOE at the time, who attacked the DOE should funding lattice specifically to support the research in the US. And the result of that is about $3 million a year that is spent buying computers very hardware-oriented to provide the infrastructure needed for this research. And this has played a big role in the lattice QC effort in the US. Many people have started their careers with observations that were done on the machine that came out of this pitch that TD and Frank made to Orbach. Research projects in Boston is a very large scale activities on the supercomputer centers in the supercomputing centers in the US are on these UQCD machines. Our machines based on two different variants, one called QCD-FE that was installed Columbia first, and then was 400 nodes and another 600 nodes at the Berkeley National Lab. This was a RBRC computer. This is a little credit card sized node that has an instrument DSP and an ASIC that we designed at Columbia. And we had tens of thousands of these nodes found together. Next thing is called this is a digital signal processor, so QCD-XP, and QCD was will see is use the DOC technology, OC technology to say, it's on a chip. So this is a picture of the nodes that when this machine, and here are two processors on each node that give enough room for a sort of 4-inch long two memory card for the node. And this was particularly influential. Not only was it taught by the University of University of Edinburgh and by the Research Center, we had altogether 3 terabytes, if you count the machine being in Edinburgh. This was also seeded in important technology advance in the US. So IBM was over, and the series of blue gene machines, BGL, BGT, and BGQ, were copies of this machine, and you can see some similarities between this code from the BGL machine. This is actually something that was given to GP as atheist today by the engineer of this project at IBM. And this is a picture of the 20 petaflops machine that was installed in March, and we have the technology that inspired by GP. So this takes up to around 2010, and I would say we had succeeded in learning how to deal with a problem of this sort, and to deal with the systematic errors that are involved, so that precise calculation became possible, where we could say with certainty what our results were. This is a very big international activity, and I mentioned, I show here, this is the important activity that's going on in China. This is a very significant part of the international effort to understand UCD and to apply that understanding to tackle important problems of physics, to see if the temperature structure functions of electron and matter will rely on calculations that are being carried out here using lattice properties of gluons, properties of exotic hadrons, and more and topic that I would amplify on is the study of theoristics, where we get to understand the standard model by comparing experiment with theoretical predictions that we can make for processes that involve quarks. This is the collaboration that I'm a part of, and much of the work that we've been mentioning is that of this group of people is really quite a large international activity, lots of different people, and many levels of expertise. As was mentioned earlier, there's lots of interest in C violation. This was foreseen in the decay to ratios experimentally measured, and they involve 2 parameters, epsilon and epsilon prime. Epsilon prime is the most interesting, is really 10% already suppressed by a factor of 1,000. There's a 1 part in a million effect. This is a direct measure of CQ violation in the actual matrix element of decay on decay, and a very sensitive place to look if one is trying to understand the standard model's theory of CQ violation, or are there additional features that we explain the variant asymmetry in the universe and lie beyond the standard model. So this is a very difficult calculation that involves these disconnected diagrams where one has a very bad single noise ratio. It's a significant challenge. This is something that we've actually been working on from 1997. Some generation of graduate students, many of them from China, and pretty significant results from 2015, true version in 2020, and a third version in 2023. This is something very actively pursued. Basically, we have a matrix element between the K meson, which is constructed by adding a certain combination of quarks that be the sync source propagators that are changed by the Hamiltonian and the two ions. So we are literally simulating a system that has single ions and neutral quantization occurs if you have a quantum mechanics box to make it hang on to two quantum states have the same energy. So we're literally calculating kind of infinite volume the decay of interest. And the experimental numbers are 16 times 10 to the 4, and the theoretical numbers are within error of that value. So this has a lot of systematic error and a lot of effort going into introducing what's essentially 20%, maybe 30% error, making it smaller so that it becomes more powerful. No visual experiments are needed. The experimental accuracy is have a way to go before we let I think quite interesting is the something that this is a big experiment evaluation is being done. There are two places where quarks are important. Even though that one doesn't involve any direct strong interactions, you want to look at into a quark loop through this polarization diagram or through this centering diagram. And this is a very large and expensive experiment undertaken because it was essentially a 3.5 standard deviation discrepancy between the standard model prediction, which was basically a theoretical interpretation of experiments, and the measurement that was done 2 years ago given the lattice calculations that have been done within the last couple of years have now completely changed that situation. The circle numbers for the first calculation done by the BMW collaboration with accuracy is the depiction of the calculation that was previously used in model prediction. And my collaborators have carried this big precision a bit better and also end in a larger result. The difference between these two results for one important part of the calculation is in fact exactly the difference between the original experimental result and the next phenomenological prediction from plus minus annihilation. So we're now at a point where I think a so-called free initiative of which describes calculations in a number of groups which demonstrate this is on a way. So the previous incompatibility between standard model prediction and measurement has disappeared. This is a rare KDK. It belongs to groups minus, which is strange to change when there's no charge. This is a strange neutral. It's a very interesting effect. It only happened the first and second order of interaction that would involve these box diagrams, which is a highly non-trivial to be able to explore. External result is really quite accurate. There's a background from two photons. So this is a third electrical wave process. This is a large electrical couple, and the absence of any additional W's or Z's is actually the same size as the interest. And a fair amount of intuition was necessary to be able to calculate this in the lattice, which makes a sort of a refined diagram of what's involved, and one makes a application in which the photons and the muon line are end up being treated in a sort of complex hybrid Euclidean description, but the two currents and the timing here is entirely in space, so it can be evaluated on the lattice. And now and this is the shortest part, and the sum should come out to be the experimental part if the standard model prediction is correct. So it's an interesting thing which has come a long way and is almost is a very standard, regular process, standard model, but it is measured accurately experimentally. And the question can be predicted with equal accuracy. It's measured some few parts per 10,000. And so in principle, this would be a very important check of the standard model. Universality, idea that first talked about in 1949, now investing into a few hundred of percent. To do that, we need to do the electromagnetic corrections very accurately. Using a method that Zhu Feng here in Beijing and Liu Sheng invented, we can in fact do it. The lattice oscillation is not very friendly to electromagnetism. Have a massive photon that can travel distances, only minor suppression. SQD requires the exponential suppression, the theory of the mass gap and mass particles. So this sort of diagram is very problematic. Absorb some fair distance off, and of course, it's far from its localized region, and it also spreads in space, and with large volume and with principle very large quantity of errors. It's very clever. It's a mixture of Euclidean and position-based and momentum methods allows us to define a box in this calculation with exponentially small corrections. So I think it's fairly likely, and continue to postdoc and work on this, and hopes that we'll be in a fraction in hundreds of percent accuracy range when this is finished. So it's exciting direction. Started off with these very active support, and we're driving from very rough numbers to now increasingly precise numbers. But it's fair to say that TD's vision and creations and guidance play a large role in this material that we're exploring. I remember he also wrote about the theory. You have mentioned that, so you have any comments on those directions? That was very interesting. It has had other consequences. We and work on this. At the same time, we started this computer construction business, and the road as it was is very appealing to the strong conversation where the lack of rotation violation was appealing. It's a very difficult formulation on a computer. So ultimately, really accelerate this particular version. But certainly, people were interested in conformal symmetry all last taking this up again. So I think that was an influential work. So there are more questions. Yeah. Very nice. I think about using the CPU clusters. Okay, the parallel. You have a plan to move it to GPU. So I would say that all of the calculations we're doing now are done on GPUs. I made an important statement after another 12, so we're no computers by ourselves. The part of spending $500 million on huge machines that we could easily get access to. There was no way to compete. So research I've been talking about is all done on commercial machines, creating machines, IBM machines, machines that they use, and all the large calculations are done on GPUs. We have really fancy code with very performance portable, and we have very performance on GPUs. The work machine that are different examples that we're using reasonably heavily now.
Okay, thank you again, Norman. Thank you. And let's move on to the second speaker of the session. Professor Shringo from app. It's going to last sorry, from Professor T. First of all, I want to thank just for giving me this precious opportunity. It's very important event, memory of Professor T. For me, I have very fortunate to directly contact Professor T, but I do benefit a lot from what he has done in his life to the physics community in China, also science education in China. So today I want to share with you some stories about neutrino physics I have learned from the research and the lectures of IPLA. So I hope you find it interesting from this story. Finally, we will give a brief future prospect for neutrino physics, which is of the main concern by Professor Lee. Let me first set up the background of our discussions. This is an important day, the January 15th of 1957. On this day, two papers were received at the physical review from the two concerned groups at Columbia University. First one led by Professor Fu and Dr. Abla. They discovered property validation from the latest theory of cobalt-nuclei. The second group, led by Professor Lehman, they measured the property violation from high and unique case. So these papers are examined and published. The paper by molecularly also measured this property violation from high unique case. This morning, Professor T gave a very clear presentation of the property violation, so I don't want to explain this capability case of cobalt. In brief, if parity is conserved, you will see the angular distribution of the electron for the case of cobalt 60 doesn't depend on the population of the nuclei. However, what we observed in experiments is that the electrons are preferably emitted from this direction anti-parallel to the productivity of the nuclei. So it's a clear signature of parity violation. And also discuss with parity violation in the interactions. So everybody knows that two components of the this paper. Actually, this paper was also published on Harvard. And this first paper was published on Harvard in 1959. This is 57. In this paper, you notice that it's a paper submitted on January 10th, 5 days before the press conference at Columbia University. There is one floating paper. The authors wish to thank Professor Su for informing them of the progress of the experiment. That means we know this discovery of parity violation in the digitally and from this actually by
Harvard University. Actually, during the summer of 1956, the same time as this first paper written by Li Yang about the question of occupation in heating Russian, he stated that they had not only entertained the idea of two theory of neutrino, but also authenticated theory, but they felt it too rash to publish it for the violation of parity conservation was experimentally observed. So, waiting for the experimental confirmation of the parity violation and then submitted the paper. Why it was submitted by general because the experiment was completed that day. So people know the new results from the experimental observations. Another thing, there are two papers about the two component theory of neutrinos in the same year. So I'm not know. But actually, we know that the reality is that they were waiting for the experimental results for parity equation. If you look into the paper, there are four points from this paper. The first one is neutrino and anti-neutrino are not the same. Second, neutrino mass is zero. Third, parity should be violated, otherwise this theory is not true. The final 5 points there is parity is also violated, but speed can be preserved. So these four points in this important paper. So what we know the neutrinos is certainly violated. It's very defined three categories of physics process, little case, high case, muon case. In each category, both the list the possibility that you have left-handed neutrino, right-handed anti-neutrino in the paper. So it depends on the experimental verification if neutrino is left-handed or right-handed. Neutrality of neutrinos was actually measured in this experiment. And it was found that neutrinos is left-handed or the helicity is negative in this paper. So it's not only neutrino is left-handed, it's left-handed neutrino participating in weak interaction means that we have E minus A form of weak interactions. At the same time, two independent groups propose that both fermions participating in linear interaction should in this V minus A form. So this the theory of the universal Fermi interaction, the V minus A form, which is exactly the same form as Young proposed in this decomposed neutrino theory. The two-component neutrino theory was actually incorporated into the standard model. So in the Starbuck paper published in 1967, find the left-handed neutrino together with the left-handed electron as a constitutional operate incorporated into the standard model. So it's fair to say that the two-component theory of neutrino had a great impact on the establishment of the standard model particle properties. Second story is about the second type of neutrino. I found this story from this report, which is actually the research profile written by Lalli about special class. So in this report it was mentioned, and you can find this story in other papers. He at the time at the Political Physics Department in 1959, he